Morning, good afternoon to everyone, and welcome to the second day of the online course on modeling software for transient flows. My name is David Ferras from the University Polytechnic of Cartagena, Spain, and together with Professor Elena Ramos from the University of Lisbon, we'll be chairing today's sessions. To warm up, let me share briefly the program. So now I'm sharing my screen. Yesterday, Mohamed Ghidawi gave this introductory keynote, which was followed by Anton Slice, who focused on the modeling of transient flows in the context of hydropower schemes. Then Brian Carney and Brian Saint focused on water distribution systems. And finally, Hanif Chowdhury focused on the more in-depth in the art of modeling transient flows. Today, we have three speakers. The first one, Yuwen Chen from Wuhan University, who will explain a 3D CFD approach in the context of hydropower. Sam van der Zwan, who will explain Wanda, which is a software for waterhammer modeling developed in Deltares. And Christophe Nicolet, who will explain Simpson, which is also software developed during his PhD and also maintained by Power Vision Engineering. Before moving to the first session, I would like to give thanks to the sponsors of this course, Deltares, Bentley, and Power Vision. Notice that two of them are speakers today. And also, I would like to give thanks to the China Society for Hydropower Engineering and Centro de Estudios Sistemi Hidrici, who are national associations also supporting this course. Said that, I hope you enjoyed the day, and I would like now to pass the word to Elena Ramos. Thank you.
Okay, thank you very much, David. Okay, you are in the second day of this interesting course on modeling transient flows that allows the transfer and the share of knowledge from those who already have a long experience of research and applied engineering to these new attendees, researchers, and those curious about hydraulic transients. Well, now I will give the floor, but before this, let me introduce Professor Wongyang Chen. He's professor from Wuhan University, has expertise in different fields, namely hydraulic machinery and system transition processes, numerical simulation of complex flow fields in hydropower engineering, pump storage, power generation technology, and computational fluid dynamics. He belongs to different technical committees, namely the Committee on Hydraulic Machinery and Systems, Committee on Fluid Mechanics, IAHR, IAHR, Joint Committee on Urban Drainage, Committee on Eco-Hydraulics, and IAHR OI Co-Committee on Higher Education and E-Learning. Okay, Professor, please, we can start.
Thank you. Ladies and gentlemen, I'm Yongguang Chen from Wuhan University, China. Today, my topic is three-dimensional CFD simulation and applications of transient processes in pumped storage and hydropower stations. My presentation includes 5 parts. First part, background and motivation. We know that the pumped storage power stations pump water during a period of low electricity demand and generate power during peak demand, acting as the regulator of the new type power system. Since the fifth 5-year plan, China's pumped storage capacity has entered a period of explosive growth. the installed capacity is expected to reach 3 times the current one by 2030. Hydropower and pumped storage power are becoming more and more important. They are the key supports for integrating new energies, ensure the stability of the large power grid, and achieving the dual carbon goals of China. To undertake the task, pumped storage units need to start up and shut down frequently and operate in off-design conditions in long periods. There are more than 5 stationary working modes and more than 10 transitional processes. Single unit normally starts and stops more than 5 times a day. Some pumped storage power units start up and shut down more than 10 times a day. For example, one hydropower station adjusts power 8 times within 30 minutes. The regulation rate of power reaches over 150 million megawatts per minute. The new operating conditions make the water hammer in the pipelines higher, the pressure power systems in turbine larger, the vibration of the unit aggressive, and the blade fatigue damage prominent. In Transient, pressure power systems, vibrations, and fatigue damage become severe. Many transient-related problems happened in the operated pumped storage and hydropower stations. For example, abnormal vibration, excessive water hammer, synchronization difficulties, power swing, and even serious accidents such as runner lifting up and rotor stator crash. Most of the problems happen in transient processes. To find the reason and the solution to the above problem, many basic questions must be answered. Question 1. What are the evolution and the interaction mechanism of fluid pattern, pressure power systems, runner force, and microparameters of turbine in transient processes? Question 2. What are the occurrence mechanisms of water column separation at the draft tube inlet under extreme working conditions? How about the role of pressure power systems? These are also important because the setting elevation becomes lower than 100 meters than the lowest tail raised water level. Question 3. What are the evolution laws of the clearance flow and the force in transient processes? How they contribute to the imbalance of runner force and vibration? So, part 2, 1D 3D coupled simulation method. To answer the questions in the last section, some new numerical simulation method that can consider the influence of flow patterns, pressure power systems, and runner forces are needed. Thus, we proposed and verified a 1D 3D coupled simulation method since 2012. The basic idea for the coupling are as follows. The waterway system, which has one-dimensional feature, is represented by 1D pipes served by MOC method. The local structure and machine, which have three-dimensional features that are important, are modeled and solved by three-dimensional CFD, providing flow fields. We have two approaches to model the water hammer waves in the three water body. The first one is defining the pressure-dependent density in CFD, namely dPdD. From the water state equation, obtain the density formula by solving the ODE. We have this formula. The second one, modifying the ideal gas law in CFD. Based on the similarity between water and gas, we can obtain the density formula by borrowing ideal gas law formula. These are the derivative process, and we can just input the pressure, reference pressure, and gamma in CFD software. These two approaches were verified by simulating the direct first phase, last phase, and negative water hammer phenomena in a single pipe system. And we find that they are all accurate. However, defining pressure-dependent density has more clear physical meanings and is more reliable. About the data exchange between the one-dimensional part and the three-dimensional part, we also proposed two approaches. One is the partly overlapped coupling, POC. The grid are overlapped here. This is the one small ridge, section 1 to section 2. Delta X in the one-dimensional domain exchange Q and H by using both C plus and C minus characteristic equations. With C minus equations calculated from the three-dimensional domain. This needs 5 steps. The other is the adjacent coupling. It changes the Q and H by using only the C plus characteristic equation. Need to calculate Q and Q at section 1 of the next step by water momentum equation from section 2. This needs 7 steps. We verified the data exchange approaches at the interface by using the single pipe water hammer and surge tank waves. We found that these two methods are all accurate enough. However, the partly overlapped coupling is simpler than the adjacent coupling in implementation. We also validated the method by comparing simulated results with the results of a model test. The model test platform was for studying transient processes of pumped storage power station installed at Wuhan University. Two transient processes were simulated and compared. One is load rejection with wicket gate and ball valve not action, run away from turbine mode. Another one is pump trip with wicket gates and ball valve no action, run away from pump mode. This is the results. The red curves are the simulated, and the black line are the measured. The simulated and measured pressure history agree well. The pressure pulsation intensity are different, which tell us that it can be used to study the general characteristics. The test platform has some structural vibrations. So there, for the pressure pulsations were heavier. That is to say, the experimental platform have some problems. We simulated a load rejection transient processes of a practical pumped storage power station and compared with the method. The simulated pressure at different locations and the runner speed agree well with the measured data. Also, the method missed the pressure pulsations due to low resolution of the data acquisition. Now we can see that the 1D, 3D coupled simulation method is feasible and can be used to study the transient processes that are related to the flow patterns and the pressure pulsations. We simulated the load rejection transient processes of a practical power storage. Then part 3, mechanism of study applications. To understand the evolution of flow patterns and pressure pulsations during transient processes, we saw the flow patterns in a turbine in different working modes. We found that the flow patterns in different working modes for pump turbine are quite different in the turbine and the pump mode. The flow are smooth in all parts of the flow channel. In pump brake and turbine brake and reverse pump modes, inlet striking and outlet swirl obvious. To study the evolution of flow patterns and the pressure pulsation during the transient processes, we simulated the load rejection transient process of a model high-head pump storage power station. We found that the flow patterns and the pressure pulsations evolve obviously, and the runner axial and radial forces fluctuate violently when the working point slides into the S-shift region. We also simulated the pump trip runaway of a low-head pump storage power station. We found that the flow and pressure pulsation have specific pattern. When the working point is in different regions and the trajectory finally converges to the runaway point in the characteristic curve, because the head of this power station is only 105 meters. This is a low head station. The dynamic characteristic of pump turbine and the influence of transient processes were also investigated. We know the dynamic characteristic in the S-shaped characteristic and the sandal region are obvious, which have large deviation with the static characteristic. The latter are measured in static working condition by model tests. We found the loop dynamic characteristics in the S-shaped region during runaway for high-head pump turbines. We originally thought it may be related to the inertia in the blade channel, but when we deducted the inertia in the blade channels, the loop characteristic also appeared. So the loop becomes thin, but still existed. So carefully compare the flow patterns of corresponding working points. For example, DP1, DP5, DP2, DP4. The similar location on the reverse routes, we found that the source of the loop is a different flow pattern in the similar operation points. Therefore, the conclusion is as follows. During the transients, the flow pattern are obvious, successive, inheriting the feature of the previous flow, makes the pattern at the same points from opposite moving direction different. The succession feature creates the loop. The influence of dynamic characteristic on transient parameters is apparent. We compare two simulations. One is the 1D, 3D simulation, the red line, and one is the 1D simulation, and one is the measured model test. We found that the two methods, two simulation methods, obtain similar results and produce the runaway fluctuation feature for high-head pump turbine. But the key parameters are different, with the dynamic one in this region more closer to the measurement. The two methods obtain similar results and produce the runaway fluctuation features, but the key parameters are different. During the pump trip runaway transient process, it was found that the operating points of low head unit converge to the runaway point, while high head units exhibit no convergent runaway oscillations. Our results meet this. We found that the oscillations of low head unit is attenuated, but the high head one is not. The flow mechanism of runaway oscillation needs answer. Apart from the sign of the tangential line at the runaway point, we find the flow pattern mechanism. The attenuation is related to the backflow patterns, pattern types, and the location at a rudder inlet. For large opening, the backflow occurs on the hub throughout sides, dominated by local reservoir pressure gradient at the inlet. For small openings, the backflow occurs in the middle, dominated by centrifugal force. These are the different backflow patterns and for different heads. We know that for pumped storage system with two units share common head rings and tail rings tunnels, the smallest draft tube pressure happens in the successive load rejection condition. Our three-dimensional simulation verified the existing conclusions that the first load rejection unit shifts the head and discharge to the second load rejection unit. The large head and discharge gradient, make the lower draft tube pressure. We also find the new feature that the minimum pressure is not only related to the flow change rate of the units, but also affected by the superposition of Wertheimer wave in the draft tube and the pump effect. We find the most for most pump turbine, cavitation can occur during load rejection transients. This is a common phenomenon. The spiral shaped and wedge shaped cavities occur in runner for short period, and this wedge shaped cavity has large impacts on axial force during collapse. The blade channel backflow induce wedge-shaped cavity. The downstream Wertheimer wave compress the cavity, make them collapse, which induce high frequency pulsation on the axial force. The occurrence condition for Wertheimer separation is an important issue. We studied. We analyze the process of cavity appear, cavity growth, water column separation, water column rejoining. We found that the cavity and the Wertheimer separation in draft tube inlet influence the axial force with the rejoining impact violent. The cavity in the blade channels impact obvious of the radial force. These two impacts happens successively. How pressure pulsation contribute to the Wertheimer separation? Combining the model test and three-dimensional simulation and bubble cavity analysis, we found that the water column separation is closely related to the pressure pulsation with frequency smaller than 1 Hertz. In other words, Wertheimer wave is the dominant factor, and the frequencies higher than the blade frequency have no matter for water column separation. That is to say, we needn't consider the rotor stator pressure pulsation in deciding the setting evaluation. How about the clearance forces contributions for runner forces? We found that the clearance flow is a very strong series flow with flow velocity core region, and the velocity in the core area is 0.4 times the conferential speed of the runner. The value of the clearance force and the mean flow channel force are equivalent in the same level of value, but the fluctuation laws are different. Clearance accounts large portion of the dynamic hydraulic forces of runner in transients. Therefore, it is important and should be considered in transient study. We compare the propagation feature of different pressure pulsations in clearance channels, include the rotor-stator interaction, blade path vertices, draft tube vertex, and rotational stores, and find different pressure pulsation propagate across the clearance channel with different features. Some can induce head cover vibration, including rotor-stator interaction and blade path in vertices. We can control the pressure with change the shape of clearance space and labels location and types. Part 4, engineering applications. A recheck calculation was carried out for a load rejection channel process of 700 meters pumped storage power station. It was found that after taking account the superimposition of water hammer and pressure pulsations, the maximum pressure in the spiral casing exceeded the standard. The pressure pulsation in spiral casing and draft tube in vanillus space are higher in magnitude. After turbine goes into runaway, the ball valve must activate and close. By simulating the runaway oscillation of a 500 meter head power station, optimize the closure of ball valve to ensure safety shutdown, it is necessary to determine the good superposition effect of the ball valve closure on pressure pulsation and water hammer. In the hydraulic transient simulation of a pumped storage power station, many 1D transient simulation models have high frequency oscillation, abnormal oscillation, using many different models. Also, the fluctuation forms have different features. We reproduced the phenomena by 1D, 3D simulation and reviewed the mechanism. The fluctuating flow exchange of the two units is the reason. It is not a numerical one, it is physical one. The interaction of the two runaway units with their working points move in different directions. One in this direction and another one in that direction. In the different direction in the positive slope region, excited the high frequency oscillation. One pumped storage power station had the difficulty of synchronization because oscillation of the parameters in low head. We used the 1D, 3D simulation, revealed that the fluctuating backflow at the runner inlet is the reason. And the misaligned guide vans can solve the problem because this method disturbs the backflow patterns. One pumped storage power station had a serious power swing in low-head large power condition. We used the 1D 3D method to review that overload draft tube vertex loop fluctuation under the runner core is the reason. The compliance and mass flow gain is the main influence factor. Pressured air supply and runner core modification can evaluate this unstable flow. Another pumped storage power station had a very serious head cover vibration, and we found that the ruling vortices in the Vannish space is the reason. The frequency of the ruling vortex in the Vannish space meets the second vibration mode of the head cover. The ruling vortices in the Vannish space was not reported in literature before. We simulated the load rejection transient and quantitatively predicted the fatigue damage characteristics and found that the damage of one load rejection transient process is equivalent many hours of operation at the optimal working point, or 1.3 hours running at the speed no load. This tells us the damage during the transient process should be paid attention. We also model soft vibration and found the simulation that considers the soft can yield the vibration parameters low, more consistent with the field tests. The axis orbit of water-guide bear under different loads are closer to the measured one, with errors within 30%. We optimize the flexible start path of one large Francis turbine unit and found that the backflow at the blade trailing edge cause intensive vibration, and optimizing the opening law of guide van can mitigate the vibration. Smaller guide van opening rates is better, even if the startup is slower. We also simulated the transient flow in runaway run-on river station. The load rejection of multiple bulb turbine generated river surge wave, which disturbs the other operating unit. We found that the influence of river surge wave to operating units in large and improper control may lead to unstable. Part 5, future research direction. One might focus on regulation of the variable speed pumped storage power station. We will try to optimize the dynamic control strategy of guide van speed during transition working points. For example, soft startup and direct transition from pump mode to turbine mode. This optimization will lay the blade the damage and the transition time as the target parameters. we recently built a model, numerical model that integrates the doubly fed induction machine and convert models into speed and power control strategy. The model are validated and with the experimental test at Wuhan University, which is supported by Dongfang Electric Company. Very good agreement between the simulated and method. The other research direction include the development of a digital twin pumped storage plants to study mechanisms of problems and improve the stability. We have prepared the 1D, 3D simulation tool that can work as a basic mechanism models. Also, surrogates models are needed for large amount of working condition simulation. Thank you very much. Thank you very much for your attention. This is my talk.
Thank you very much, Professor Hyung-Kong Cheng. It was a very interesting presentation. I will make a brief overview before to go to the questions box. And it was presented the coupling of two different models, 1D and 3D models, with difficulties associated to the boundary conditions, using a partly overlap coupling or adjacent coupling. It was showed also the problems associated with runaway conditions in specific zones of the turbine, the spiral case, the draft tube, the different flow patterns in these zones with low rejection of a pump and a turbine separately during the runaway conditions. Professor Hyung showed also the hysteresis and the backflow that can happen in the blades channel. Talked about the fatigue damage associated with some vibrations and pulsation of the flow. Some power control strategy is under research, and also the digital twin. Very nice. Thank you very much again. And I think we can proceed for the part of some questions. The interested attendees can put questions on the QA box at the bottom of your screen. We have already 3 questions, very interesting questions, about the software or programming language that was used to carry out the coupled models between 1D and 3D. Yes, please.
We can use UDF, user-defined function, to implement the 1D simulation into the 3-dimensional simulation software. For example, Fluent, CFX, and other software. This is one approach. Another approach is using OpenFOAM to totally couple the 2 parts.
Yes, and the coupling between the method of characteristics of 1D size and this 3D, this boundary condition, it's not easy at all.
Boundary condition.
Do you simulate as an implicit model? Do you simulate at the same time, or do you simulate only the pipe and after this make the?
It is explicit. Exchange the Q, the discharge and the pressure between the 2 parts. Yeah.
Okay. Okay, another question. You already replied. It's about the Fluent. We can use Fluent Open Phone in terms of 3D software. Another question is unsteady friction modeled in the 1D side? If yes, in the 3D 1D coupling interface, is unsteady friction information coefficients in terms of coefficients transmitted from the 3D to 1D, considering that unsteady friction emerges from 2D, 3D nature of the transient flows? Can you say something about this, the use of unsteady friction, because you are simulating transient conditions with a lot of dissipation in terms of the pressure waves?
Pardon me. I didn't understand what is the question.
Yes, the unsteady friction, it's a coefficient to take into account the damping effect associated with the flow under transient conditions. No, you didn't use this. No.
What?
Unsteady friction.
Unsteady.
Yes, unsteady friction. We consider for the head losses, okay? And we can increment more these head losses using coefficients like unsteady friction. No, maybe you didn't use. No worries, okay? Another question is, in the last slide is very interesting. How we can prepare it, the last slide.
Last slide,
You can go to the last slide, yes. Yes. Okay. This is an expertise of Professor Wang. Team. Yes, that's right. That's okay. With the simulation of the pressure variation and the surge in the surge tank, the variation of the water level in the surge tank. It's very interesting. That's right, and very formative for the young researchers. Another question is about it was possible to synchronize the time step from 1D model to the 3D models.
Yeah. Normally, because the three-dimensional simulation need a very small time step. And for 1D, we can use larger time steps. So we can let the three-dimensional simulation many time steps, and then exchange the data with the one-dimensional parts.
Okay, we get information from
different time step.
Yes, from the pipe system. You can use 1D model, of course, and after this we get information and put inside of the 3D model. I think so. No.
Yes.
Yes, and we can simulate different time increments, of course, but in 1D, for the method of characteristics, we have the Courant-Friedrich condition, okay, to avoid some additional dissipation, numerical dissipation effects. In the 3D, we are simulating only that part, that zone, specific zone of the turbine or the water intake, for example. Yes, but maybe you transfer this information from one part 1D to the 3D, okay, using the C+ or C- characteristic line of the method of characteristics. It is not easy, of course, and can introduce some specific effects, but it's very interesting. Another question. The final question is, did you consider the unsteady friction? It is again, the unsteady friction. No, I think you
I cannot understand the meaning of steady friction.
Unsteady friction. Okay, the steady friction is the normal or usual estimation of the head losses, the friction head losses. Okay. For example, using the Colebrook White or yes, or Hazen-Williams, whatever. Okay, we can use. And unsteady friction, it is another
friction. Steady friction. Yeah. I understand. Yeah. In our simulation,
in the method of
one-dimensional, we use the steady frictional method. However, unsteady friction for the high frequency problem is very important. This is not my focus.
Okay. Yes. Understand. Okay. Another question. Can I put you one question from my curiosity? For example, in my PhD, I tested different specific speed of runners. I tested for smaller specific speed, Francis turbines with a completely radial entrance of the flow into the runner, and until to the propeller or Kaplan turbines with an axial direction. And I noticed during the runaway conditions some completely different behavior. Okay, for the lower specific speed, like Francis, okay, closed runner, will induce a peak sometimes higher than a controlled wicket gate closure. For the high specific speed or different shape of the runners, induce a suction effect and the pressure comes down. It was very interesting to notice this in my PhD when I developed some tests about this. Did you get some experience using different type of runners, not only for the head of 200 or higher, but lower than this? And did you compare already?
Yeah, we compared the different. However, the pump turbine.
Yes. The pump turbine is similar with the Francis.
The lowest head is 105.8 meters. This is 650 meters. Yes. They have different characteristics, curves, and different flow characteristic.
Yes.
The difference is for this low head pump turbine, in the runaway condition, they can convert to the runaway point very soon. And for this kind of high head pump turbine, this is the difference. The trajectory line is a loop. The fluctuation continue if we do not close the ball valve.
Yes, interesting, yes. And for lower heads, for example, 20 meters or 50 meters, no? We didn't?
No.
Okay. We have another question. I don't know if you can assess the question box. It is in Chinese. I cannot read in Chinese, unfortunately. I cannot read it, but
I cannot find the
Can you find at the bottom? You can find the Q&A box. If you open, we can see the.
I don't see. Yeah.
No, at the bottom of your screen. Q&A with the number 3 there in red. Can you see at the bottom of your screen? No. Okay. If not, you move to another one. I'm sorry. Peng Sheng, I'm sorry. I cannot read in Chinese. Another question is about the pressure pulsations in the turbine produced pulsations of delivered power, right or not? The pressure pulsations in the turbine produce pulsations of delivered power.
Pardon me, please repeat the question.
Yes.
哦，这个你来操作一下，我这个搞不了啊。
Question and answer box at the bottom of the
看
screen.
不到啊。
At the bottom of the screen.
我看不到下面啊。
The bottom of the screen.
其实看不到下面。We normally
Near the shot. Near the shot.
Zoom.
Near the shot, you can see them. Near the shot, you have another box here, another section, the question and answer question at the box at the bottom. If you can see the shot,
Sorry, Zoom is not
you are not used with Zoom. Yes,
we just normally cannot use Zoom.
Zoom.
We
Okay,
cannot find the question.
Okay, maybe Pengsheng Zhang can contact directly with Professor, I think, and can put the question. But we can move to another question about the pulsation in the turbine. Can you speak a little about the pulsation you detected during the cavitation occurrence in the draft tube?
Cavitation in turbine.
Yes.
The cavitation in
Some pulsation, with some
the
pulsation.
cavitation means occur under the core
Yes.
in the inlet of draft tube in small space and in the channel of the near the outlet. But for water column separation, normally this condition cannot be happened in actual hydropower stations.
Yes, the joining and the separation.
And in some special working points, for example, in the S-shaped region, the cavitation also may occur in the inlet of the runner.
Yeah. Okay, and I think we have another questions. Have you already published these results? Have you already published these results?
What's these results?
Results.
Did
you
yes, in our simulation we found this this phenomena, and for some measurements model tests, we can see the cavity cavitation in the draft tube because the draft tube is plastic.
Yes. Yes, a transparent plastic. Yes, a transparent plastic. You can see the cavitation and the column separation and the joining of this with some peaks. Yes. Do you have some publications about this? About your presentation.
We for several pumped storage power station, we simulated this phenomena, but we have no measures to do something. It is not so harmful in most cases.
In most cases, yes. Do you have publications related with your presentation? Do you have already some publications?
Yeah.
Yeah.
My applications, as I introduced, we solved several head cover vibration problems. For example, we found the ruling vertex in the vanillus space, and the manufacturer solved this problem by kill the ruling vertices.
Okay.
So no vibration. And another application is the vertex, the cavitation fluctuation in the draft tube lead to the power swing. We also find the problem, and the power station limit their working region, so no problem occurred. Okay.
Okay, thank you very much. We have a very interesting lab facility, okay, to study pump storage solutions. Very interesting, and thank you very much. I think, David, for now, I think it's enough. I think if you want, you can proceed to the next speaker.
Okay. Thank you very much.
Thank you very much, Professor Yong Cheng. Thank you very much.
Thank you very much. Thank you very much, Elena, for chairing the session, and Yong Cheng for the interesting presentation. So now it's the moment to pass to the next speaker, who is Sam van der Zwan, who has more than 15 years experience in Deltares in the field of pipeline hydraulics, especially in transient flow analysis. And he's member of the Technical Advisory Committee of the International Conference on Pressure Surges. He's also developer of the 1D water hammer software called WANDA, which is precisely the topic of his talk today. Sam, the screen is yours. Thank you.
Thank you, David. Thank you for the introduction. And I will share my screen. And I'm right, you should be able to see the screen now.
Yes, we can see it.
Yeah, perfect. Thank you. Thank you, and also welcome to you all, and thanks also for having me here so that I can talk a little bit about WANDA. But I'd like to focus more also on some issues if you are modeling transient flows. And I want to focus on boundary conditions and control. So let's jump into that. So first I will start with a short introduction on WANDA. And then next topic we were talking about is boundary condition modeling. So point some issues and some ideas we have about that, and also hopefully this is also useful if you're not using WANDA but also other software to think about this, how important it is to correctly model your boundary conditions. Next topics I want to talk about is the control module. I'll be explaining why this is important, why do we want to do this. And I will end there with a case where we'll talk about virtual commissioning using WANDA. And I will end with some takeaways to take home and hopefully to useful for you to use in your day-to-day practice. Okay, but let's step into it. So WANDA software is developed by Deltares. Development already started in the 70s, and of course after that it has been refactored and changed a lot, of course, due to new improvements in codes and standards and so on. And but it's already in that sense old software. But also what we did is we validated it. We have some nice lab facilities here at Deltares. We have, for example, what's called the Alpha Loop, which is a 300-meter DN250 pipeline, where we can do measurements like pump trip, valve closures. We can, but also can do measurements with air in the pipeline. We can use those results also to validate the Wanda, so to ensure that it's indeed doing what is happening in reality. Next to this lab, we also have field experiments, measurements we have performed. We also use that to validate the model. Next to that, Wanda has also a Python API, which basically means there's a Python module you can use to do everything which you also can do in the user interface, but then you can do it from a script that can make your life much more easy in that sense, especially for if you have text which you need to do repeatedly, like creating figures or something like that for your reports. You can easily program that and then use that. As I said, we developed the software at Altaris, which we also sell it. So we have about 200 plus licenses worldwide. But the main thing is we use the software ourselves. As Altaris, we also consultancy, IAHR study, we give courses, we develop, but in that we all use the software also ourselves. And that also helps in ourselves knowing the software and also further developing the software. The base of Wanda is, of course, the water and that's based on the method of characteristics. No need to explain that. Everyone is familiar with that. But next to that, we have an extensive library of other components like pumps, check valves, air valves, search vessels, T and Y junctions. And in that sense, you can model a wide variety of systems with Wanda. We also have, for example, also a model of a turbine, so we can also do simulations with turbine. I'll be talking a little bit later about also the control module, which we have integrated into Wanda, where you can model a control system which you couple to the hydraulic system to simultaneously simulate that. And we also have an extension where you can also include the temperature and also the effects of the temperature on fluid properties like changing of density and viscosity. And the most prominent use case is district heating systems, where of course you have a varied temperature. And we'll be talking later a little bit also on that. This especially in the Netherlands, but I think also worldwide, this is important because of the energy transition, where we see tendency to go more to district heating systems for the heating of the houses. Finally, we also have a module which you can use to model the batch transport of slurries. And those are not only Newtonian fluids, but also non-Newtonian fluids, which can be included there. And you can model that you have one batch of one type of fluid and a batch of another type of fluid, and then that's transported to the pipeline. You can also have water hammer waves growing through these slurries, and of course, then it will have some effects if it goes to the boundary of these two slurries because of the different fluid properties in both slurries. You can also model that with Wanda. So it's a little bit about the basic of Wanda. Later on, I will be also showing the software. Here, by the way, on the right-hand side, you see the component library of the couple of the liquid components we have. Okay, but let's go into the boundary condition modeling. So you all know the method of characteristics, where you have the grid, and according to the characteristic equations, you can calculate the head and discharge or other quantities of what you're using on all these connecting points. But to be able to do this, you first need an initial condition, so your starting condition with pipeline. But you also need boundary conditions. Basically, boundary conditions, those determine basically what's happening, because those boundary conditions will change the pressure or the discharge, and that will travel into your pipeline according to the characteristic equation, according to these lines. So if your boundary conditions don't do anything, nothing will happen in your pipe. But also, if your boundary conditions are not correct or not correctly modeling the physics, you get pressure waves, but the results will be completely wrong, not physically correct. So yes, the method characteristic is important, but I think that's well known, and there are some details like what we talked about, the incentive friction or the viscoelastic effects, which are also important to take into account, but more important is basically the boundary conditions, because if you don't have those correct, you mess it up. So the boundary conditions are crucial for correctly modeling your system. And that also means that as modeler, so if you're using the software, you should understand how these boundary conditions have been implemented and what they mean. And this is a general remark. So this is not only for Wanda, but also for other software. If you want to use other software, you need to know, okay, what is this component doing? What is the physics behind it? And is it modeling the physics which I expect to model? Yeah, that's important to know, to remember and to keep in mind. So just don't start using components like, okay, I think I know what it's doing. Also check what the component is doing. Yeah. So to make it a little bit more clear, we're going to look at some examples. We're going to start with a simple wastewater system. So what do we have? We have a pump, pressure pipeline, 5,000 meters long, it's an inner diameter of 500 millimeters, and it's transporting the water to a wastewater treatment plant, and there it comes into a reservoir, and the reservoir has a weir at a certain level at 5 meters, and then it's just discharged into wastewater treatment plant. And what we want to do, we want to know, okay, what happens if this pump trips? What can we expect for pressure waves and minimum and maximum pressure in the pipeline? But we don't have the characteristics of the pump yet. We are really early in design, and we are smart enough to think about that. So we need to know, can we model this? Okay, so let's start doing that. So let's go to Wanda. So for those who have never seen Wanda before, Wanda has a user face which is a PNID-like look and feel. So we are not map or GIS based, but more like a process flow, process and instrumentation diagram. And in this diagram, you build your model. You see on the right-hand side here, you have all your components, different libraries where you can choose from. And if you click on a component, get here information on the component, you get the input properties and the output properties. That's basically how a model is built. And what I did, I built here 3 different type models of the same system. So here in the center, we have the pipeline, and all the pipelines has the same property. It's just a pipeline with a diameter of 500 millimeters and a length of 5,000 meters. But then, as you can see, we have different types of boundary conditions used. So here, this one with the H in there, that's the constant H boundary. So basically, it's a boundary condition which keeps the head constant. And of course, you can vary it according to an action table in time. The one on the bottom at number 3, that's constant Q boundary, but that keeps the discharge constant, or it varies it according to action table specified by the user. We have one final boundary condition here, that's the typical weir, which is an upstream storage. So what you can see in the picture, basically there's an upstream storage and a weir at a certain height with a certain width. And basically based on the physics of the system, so the head and the discharge coming into, calculates the head above the weir, so they have a certain water level in this upstream storage. That's how it's working. And back to what we are doing. Okay, that would be basically what we have. So that's why, so we can just use that component. But let's also have a look at this component, because here we put at the downstream boundary just a constant head boundary. We want to see, okay, is this an appropriate choice or not? To get an idea on that. Yeah. Oh. what of course we're first going to do is look at some steady state results. So what I'm going to do is I'm going to run only a steady state simulation. So of course, that's always the starting point. And in steady state simulation, we always simulate that there is no changes in time, but that we should have constant head and constant discharge. So then we're going to look, for example, with this pipeline, look at the head, this pipeline. And we see, the pipeline is at 0 meters, but we have the hydraulic rate line you can see here went from 40 meters to approximately a little bit above 5 meters. That's logical because the weir level was at 5 meters, and then you get a little bit of water above it, so it's a little bit higher than 5 meters. But then we're going to think, okay, what we're doing, we're very, very initial state. In this one, we just set it to 5 meters. And we're going to look at the same graph for this one. You can see it's almost the same for the second model, the purple line. Only there's a small difference here at the end, but I would argue that that's negligible. So basically, for the steady state, these two models are approximately the same. So let's see at the third model, because the difference is here, instead of setting the head on this side, we set the discharge to 700 meters. And again, and plot the head. Put it in again. Now the green line is almost on top of the other ones. And if you would look here in the model, you see also some of the results. You see the discharge varies a little bit. And here the head at the beginning of the pipeline, here it's 13.98 meters, and this one is 40 meters. So again, the difference is so small that it is negligible. So basically, looking at this, and we can say, okay, steady state, all of the models have the same behavior. So for steady state simulations, you could use any of these models. There's no preference. But of course, we want to do a transient simulation. And we want to do a trip of a pump. So now we need to think, okay, if the pump trips, what happens? Basically, the motor torque is stopped, but the impeller can still keep on turning due to the polar moment of inertia of the pump. So what we could do, we can say to this action table, we can say, okay, we can just decrease the head to 0 meters. It's the suction level in this case. That could be a proper approach. What you could also do, if you go to this bound Q, instead of saying the head goes to 0, we say, okay, the discharge goes to 0. And of course, the question is, okay, what is the correct modeling for a pump trip? Should we decrease the head or should we decrease the discharge? Before I'm going to answer this question, I give you a couple of seconds to think about it yourself, what you think should be the approach. Okay, before I'm going to answer that question, we are first going to look at the other boundary condition, because we have here two boundary conditions. We have the weir and the constant head reservoir, and we just saw that, okay, there's not much difference between them in steady state. So we want to know, okay, in transient, what's going to happen? So what's going to happen? We drop the head here, pressure is traveling here, and of course then it reflects on this reservoir, but what will happen here is that some backflow into the pipeline from this reservoir. So the water level here will drain a little bit. In this case, what will happen is, of course, this is a reservoir with constant head. So if the pressure waves come in, it just will reflect and it will start also supplying water, but the water level will be kept constant. So let's have a look here. Let's create a time series. Run, of course, transient simulation first. So we have a time series of the head at the weir. Of course, I can also add time series of the head at the constant head reservoir, but that's of course constant, 5 meters. But what we will see is that, yes, the water level is dropping, but dropping about 35 centimeters. So that's not that much. As we know, this pipeline is at 0 meters. Basically, it's a flat pipeline and then going up. So it's also not draining the pipeline. Basically, only this reservoir is draining a little bit. So I would say that for this boundary condition, you could choose to say, okay, let's keep it at a constant head. Of course, it becomes a little bit different also if you start draining the pipeline, but then you need to take a little bit different approach to model that, because you need to take the area of the pipeline also into account. If you have only a small change of head, then you would argue, okay, this is a good enough approach to model it. Okay, then let's jump to the other one. So what happens here? Look at the time series. You will see that the head is dropping to 0 meters. What will happen now, of course, is that the discharge will start to decrease over time. Of course, it will decrease, then you have to wait a little bit. The pressure wave is traveling into the pipeline, reflects, comes back, and goes up. So if we could start looking at chart of the location, a little bit bigger. See here, the blue line is the initial head, orange line is the minimum head. And I can also play a movie. I hope this is a little bit visible. What you see is the pressure wave is going into your pipeline, reflecting on the boundary condition, and then the pressure wave is traveling back, of course. So if you have done simulation before from pump trip, this looks okay. It looks similar to what pump trip is doing. And of course, it's logical because the pump trips, then power is lost, but still water can be supplied through the pump. Basically, only your head drops and not your discharge. So what would happen if we, instead of dropping the head, set the discharge to 0? Now to look at the head then, because basically what is happening is you change your discharge, basically velocity, to 0 in a short time. So then you get also your pressure will drop. As you will see here in this graph, pressure even drops up to cavitation. So it cuts to cavitation immediately. At some point, the cavitation implodes due to reflection. That results in very high pressures here, up to, in this case, about 100 meters, so 10 bar. Again, we also can look at time graph. Let's restart it. You see here the pressure wave coming in and immediately going, bringing the pressure to cavitation, and it reflects that implosion of cavitation. Very good to know that in the 70s, 80s, the tests have been performed at Deltares to test also with cavitation, and one has validated also against that. And at some point in time, then there will be a huge implosion and the pressure will rise very high. Basically, this shows that for a pump trip, basically setting the Q to 0 is not the proper way to go. This would be more like a valve closure, a sudden valve closure at the beginning of your pipeline, because then basically, if you close the valve, the valve becomes 0. And you cannot have any discharge anymore. So it will be more reasonable approach. You see it imploding a huge pressure wave coming into your pipeline. And of course, reflecting back. So, but thinking about the moral of this story is that, again, you need to know what you're doing. Because if you don't know what you're doing, then you would say, okay, this is a correct model. You steady state it is correct, but in transient, you get huge pressure waves. And then you think, oh, I need to do something about it. Well, in reality, it's much less severe. You might need to do much less. So again, know what you're doing, because then you choose the proper boundary conditions, and then you can do make the model the proper assumptions or the proper conclusions based on your work. Okay, so that was on the wastewater system, but of course we can also look at the drinking water system. An example of a drinking water distribution net. You have here pumping station, one pumping station, and that is supplying water to all these little triangles, which are simplified models of households, so basically aggregated households, which have a certain demand. But then the question is, okay, how should we model this household? So what we want to do is not an extended period simulation. We want to do transient simulation. We want to see what happens if these two pumps trip, pressure is going into, and at the end of the question is the question, to an acceptable pressure occur in this system. But for that, we need to have an accurate model of the boundary condition. So, what choices do we have? Of course, you can think of a lot. So I have listed here a couple. Let's go through them. So what I can first think about, okay, yeah, this is thinking about a distribution network. Okay, then we have a demand pattern. Maybe you know APANET. You have this demand pattern, which is basically followed discharge over time. And you have this nice two humps pattern. So about 7, 8 o'clock, you have the first high maximum, and then decreases, and then during 6, 7, 8 o'clock at the night, you have the second bump, then it goes down for the night. So you could say, okay, yeah, we can do that, but this pattern is basically an hourly pattern. But what we're going to simulate here is seconds, maybe minutes, not hours. Because these pressure waves, of course, go very fast through your pipeline, as we know, depending, of course, on the pipe material, but even for PVC pipes, it goes still with hundreds of meters per second, which is still very fast. So we only need to simulate seconds, so we don't need to simulate hours. So in the seconds, this pattern, this discharge is not varying due to this pattern. So using that approach, that, yeah, is not the proper approach. Okay. Of course, we can use this pattern to say, okay, I want to do simulation at minimum discharge, and maximum discharge, and average discharge. That's a good use of this pattern for water armor simulations, but we don't need to simulate it for the whole hourly, daily pattern. Okay, then we said, okay, we can just pick one discharge, and we can keep it constant. Just so, okay, here we change it, keep it constant. But okay, let's have a thought about it. Okay, what's happening in the system? The pumps, basically, they supply pressure to the system, so that it's pressurized. But when they trip, what happens? The pressure drops. And what happens at your house if your tap open and the pressure drops in the distribution network? then, of course, the discharge also will change, will drop. So keeping the discharge constant is also not a good approach, because then basically what will happen if you keep a constant discharge in this network, basically all the water will flow out and it will become fully vacuum in the network. So, and that's not realistic, of course. Basically what will happen is that if the pressure drops, also the discharge will drop. So, okay, then maybe we should use a constant head boundary. Okay, you can use constant head boundary, but then if we're using constant head boundary, then what pressure should we set? Because if we're going to set the pressure in the net, located in the network, then we're fixing that, and then we will not see any pressure waves coming in to the network. But that's also not the proper approach. So, but then we can set it to atmospheric pressure, but then we get in all these nodes, we get atmospheric pressure. So that's also not completely correct. We should do something a little bit more elegant. Because what we know, if you open the tap, you still have a head loss between the main pipeline in the street and your outflow, because your outflow is at atmospheric pressure. There's a resistance in between. We could model that simplified, very simplified, just neglecting all the pipeline in the outflows. Could simplify it by using a valve. And by setting the resistance in such a way that the initial discharge matches with the discharge we want to set. And then we can set this pressure to atmospheric pressure. And then when the pressure in the system, in the main pipeline drops, what will happen due to the resistance? Also the flow into your consumer will drop. And that's, of course, the physics we want to capture. So, and since we only have use one discharge, we could also say, you can just put a resistance instead of a valve there. And what we have done in Wanda is we created one component out of this, it's called the cap. It's a nice triangle on top of it, where you can set an initial discharge, and you set a downstream head, and those two combined will calculate an initial resistance based on the pressure in the system and the head loss and the discharge, and that is set. And then if the pressure drops in the network, then also the discharge to the tap will drop. So how does that look like? Let's go back to Wanda. Here we have this model which I just have shown. If you have a pumping station, of course, what will happen is that with the pumps, in the pump speed, you trip the pump, so the pump speed will decrease. And then you can see here, you look at the head, for example, you'll see that is dropping, and then due to reflection, of course, it's rising again. And then let's take, for example, this tab. Let's have a look at what's happening there. So we can look at the head. So this is the head in the system. See, due to the pump trip, the head decreases. And if I then look at the discharge, and it looks a little bit strange because the discharge is increasing, but that's because the discharge is negative. So actually the absolute value becomes smaller. So if the pressure drops, the discharge to the tap will decrease based on this resistance, this valve which is there. And of course, we can also create a nice graph. What's happening here in the system, maybe you can go there. And we get at a location chart, and then I can make a movie out of what's happening in the pipeline. See the pressure wave coming in. And at some point you see also, due to a loop system, also at other points, pressure waves coming in. That's why dropping sometimes very rapidly. Here you even have cavitation. So you might argue that the system is not well protected, especially for drinking water systems in the Netherlands. We don't want pressure to drop below atmospheric due to the risk of intrusion of groundwater. So again, we see, okay, for modeling of for the distribution network, you need to know, okay, what can I use? What components can I use to accurately model that? Okay, let's then jump to the last boundary condition example. That's coming a little bit more solid. It's our district heating system. You see here below, simple system. So we have one source, which is basically here, which supplies heat. And then we have the pump and the check valve. Then we have a supply pipeline. Then we have a heat transfer station. Basically, we're modeling here the primary grid. And basically here you would have the secondary grid, but we haven't modeled that here. So we only model the primary side. Basically just takes heat out of the system, and then we hear the return pipe. And then it's good to note that, of course, this supply pipe is at a high temperature. So for a conventional heating system, it might be 100 or 120 degrees Celsius. And this return pipe might be at something like 80 or 70 degrees Celsius. So there's a temperature difference between those two pipelines. Why I mentioned that? Because that can be important, because that will have an impact on the properties like density, but also on viscosity, but also on bulk modulus of the water. And that will, at the end, will influence also your wave speed. And that again is important if you're going to simulate, that you use the correct properties for that. Because otherwise you might have mistakes, your overpressure criteria triggers might be triggered if you don't do it correctly, if you don't take it into account into your simulations, because in reality it is there. And colleagues of mine have just published a paper, and it's in applied thermal engineering on this topic. It's called Temperature Effects on Water Hammer Phenomena in Pipelines. And probably this presentation will be shared, so there's a link also to this publication. So, but yeah, that's why it's important to take that effect into account. But the other thing is that, as you see, it's a loop system. So yes, we have boundaries like the pump, the check valve, but we don't have a start and an end boundary in the system. And basically, that's a little bit more technical, is that in steady state, so look at that, all of these components will give an equation which says something about the head difference or the pressure loss and couple it to the discharge. Because you have a kind of a loss equation in there. Same goes, of course, for the pump, because there's a relation between the pump curve between the pump head and the discharge. Now, the same for all the other components. So basically, if to try to solve this system, the problem is that I have infinite solutions, because I can set the pressure here at 1 bar and I can solve the system, but I can also set it at 2 bar, 3 bar, to put it every value, and I still have a valid solution for the system. Because all the equations which those components give are met, are satisfied. So we need to set somewhere boundary for the head and the discharge. So how do we do that in Wanda? I have this example. Oh, sorry, it's the wrong one. Of course, prepared the model for this. Same model. Basically, what we do for that is that we say to a node, can change the type. We can say, okay, you have an initial temperature or initial pressure and temperature, or a conditional initial pressure or temperature. The last one, basically, it only predescribes it when it is needed. That's what we use. So I have here one node where I say, okay, you can predescribe your pressure and temperature if it's nowhere else in the system described. You have a value of 10 bar, and if the temperature is needed, then put it at 120 degrees. So Wanda in calculation core can find, okay, I cannot solve my equations. I need matrix becomes singular, basically. Okay, I need to set somewhere the pressure or the temperature. And then it uses this node. That's basically the trick we use. And of course, we only do that when needed. And also in Transient, we don't do this anymore. Then we just use the value of the previous time step if needed. And then for this case, it's not needed because then we still can solve all the equations without setting it. And as you can see, now you see we also passes back a message. Okay, pressure is set to the initial pressure. So having said that, of course, okay, then I run a model. So that's a steady calculation. Then, of course, we can also look what's happening in the pipelines. So we have our supply pipeline. Then we have small head loss due to the resistance, due to the heat transfer station. And then we have the return pipeline. And here we can also, because also we're doing it in Wanda heat, so we have temperatures. You can see the supply line is almost constant at 120 degrees. Small change due to losses, but since the velocity is relatively high, there's only a very small temperature change. And of course, what we also can do, also interesting, is of course to do a pump trip. And then we trip the pump. And what we will see then is that, of course, when the pump trips, what will happen, that we all know from normal systems, is that you get an under pressure, negative pressure wave going into your downstream pipeline. But in this case, we have a looped system. So we get an under pressure, negative pressure wave going into the supply pipeline of your district heating system. But it's all connected to, there's no reservoir here. And sometimes there's an expansion vessel, but we didn't model it here. So what will happen is the pressure wave will also go into this pipeline. But that's not a negative pressure wave. So decreasing pressure, it's a positive pressure wave. So let's have a look what's happening. And you see indeed we have here negative pressure wave in the supply line, and here positive pressure wave in my return pipeline. What you will see, they will traveling through the pipeline, just continuing until they reach the heat transfer station. And then it almost looks like they will be flagged, but it's not the case. This pressure wave will just go this pipeline and superimpose on this hydraulic gradient, and this one will go superimpose on this hydraulic gradient. You also see I changed the wave speed of this pipe, increase it a little bit, make it a little bit faster than the return line. So this one goes already a little bit into the return line. They don't come at the same time, same place at the heat transfer station. And this will, of course, they will keep traveling not back and forth, but basically through your pipeline, round and round. And of course, they will dampen out at some point. Here you see also why it's important to look, because here pressure is a little bit lower than you would expect. So it's important to take this temperature effect into account. And you also see that it's quite capable also of simulating a loop system. And then it's important to have this initial condition correctly to start from, because it, of course, it will matter if you start at 10 bar or at 5 bar, gravitation purposes. So I talked a lot about boundary conditions. We saw different systems. We saw a wastewater transport system. We saw a drinking water system and also a district heating system. which all have their own characteristics. But the main finding is know what you're putting into the model. And know different components and the physics they are modeling. Modeler, if you're using software, you should know that. And a side step for Wanda is of an extensive help. So if you have a component, you can click on this help button. This is nice big, but here the mathematical model is explained and all what the physics is behind it and how it is modeled. So you can always find that for the Wanda software. If you find that really important, because then you have access to this, you can look into that. And of course, if you don't understand, you can always ask us to help you in that sense. But also, if you're using other software, the same applies. Know what you're putting into your model, what is it doing, and is it modeling the physics I want to expect? I expect to model. And next to that, always be critical at your results. Don't easily trust your results. Always be critical. Ask yourself, okay, do I understand what's happening? So I hope all of you will take this along and put it in practice. So then we can go to the next subject is control loops. Completely different subject, but also important. Because a pipeline system will always be controlled by a PLC, which probably will control it on the pump under pressure, or there will be some controls like, okay, we need to switch down the pump when it reaches a pressure threshold, or we need to close a valve, or we need to close the valve immediately when we have a pipe rupture, and so on. All of these kind of questions. And why do we want to do that? Basically to verify it. Okay, because these controls will have an influence on your hydraulics of your system. There's an interaction, and you need to check that. And for very simple systems, it might come away, but we see also much more complex systems. And then it's really necessary to verify basically your operational control philosophy, your procedures, like your startup, your shutdown, to ensure that if you start a system, then start it correctly without triggering any emergency triggers and so on. But also to avoid that you get interactions between components. So if you have multiple components which are controlled, you should always check if the control of the one is not influencing the other one, which can result in interactions and fluctuations, and that can be very dramatic for your system. Especially this is important for if you have a booster system. If you have a booster which is switched off, switched on, then you need to check that. And finally, what the advantage of doing, you can also have already insight in the parameters for your PID controllers. So you have there two parameters, because normally you're only using P and I, not a D. So you have the gain and integration time. By doing the simulations, you can already have an estimate of them instead of going into the field and playing with it and turning like, okay, gain one, changing it a little bit. And check and already have a good estimate of the parameters to use. So if we're talking about control, we need to have common understanding of a little bit of the terminology we're using. And first of all, we have the controller. The controller is a device or software that calculates an actuator value. Okay, then we have, of course, a new word, the actuator value. So the actuator value is basically an input into the system to a device that carries out an action. So, for example, the pump speed or the valve position. Those could be actuator values. So basically, the controller calculates how it does it. That's free, so just do a calculation, and gives out an actuator value. You also have a controlled quantity. Basically, that's a quantity that's controlled by the controller and the actuator. So, for example, a level in a tank. You have a valve which is controlled to reach a certain level in the tank, or more in your houses. You have your thermostat, which you set to a certain temperature, then the control system is going to actuate your heating system or your cooling system, depending on where you are, to reach this temperature. There you also have a control system. So to make it a little bit more practical, here's some examples, which are of course not that difficult to understand. So we could control a level in a tank. We try to control it at a constant level in a tank where we have a constant in and outflow. For example, you have the inflow for a certain pattern. You can try to control the outflow, that keep it at a constant level. Or you switch off a pump or a valve when it reaches the upper or lower limits. So, for example, example of that is a wastewater transport system. There, if the water level in your pump sump reaches a certain level, the pump will start. And if the chamber, the pump sump is drained, then it will stop. And of course, you can also build combinations. Of course, you can also control the flow in the pipe or try to pressure at a certain level. There's a lot what you can do. If you're going to make the step then towards Wanda. In Wanda, the control system consists of 3 parts. You have the sensor. If you look here below, that's basically this circle with this line under it. 2 dots. That's basically a sensor, and the sensor can measure a quantity. It can be the pressure, the head, the discharge, and depending on where you connect it, you have different choices to measure. Basically, all the output Wanda calculates can be used as can be measured by a sensor. And the second part is you have control blocks. So those are these components. Basically, those are the control components. Those are basically, if you go back to the definition, the controller, because it gets some controlled quantity, and that does the calculation. And you can connect this control components to each other to build a more complex control system. And then finally, we have the signal lines. Basically, the signal lines are basically the connection between all the control components, but also from the control component back to the component, the hydraulic component, to the actuated component. So, for example, back to the valve, to say, okay, what the valve position needs to be. And here, I'm not going to show in detail all of these controls, but these are the control components we have. Those come in groups. So if we have conditional actions, like a simple condition comparing a value to see if it's less or equal, greater, equal to a certain value. Also, we have level control switches. It's more like what I talked just about this wastewater transport system, where you have 2 sump levels, one to switch on and one to switch off, and you would use a level control switch. Here we have also several continuous controllers, PID controllers. And we have some what we call generators. And generators are basically you can create a sine function, or just a constant function, or follow just a table. Then, of course, we have our logical operators, like the AND, OR, NOT, exclusive OR, or logical delay. Finally, we also have some numerical operators, so we can we have a summation, subtraction, multiplication. Those are like we take the absolute or the sign, so on. So basically, you have here a lot of components which you basically can build a complete, extensive control system for. Finally, we have also 2 components, one to read from a valve and one to also write to a valve. So as you can see, it's a very extensive library, but again, you should always build it slowly and also check always to ensure that you know what components are doing. But let's go to a example to make it more clear what you can do with control. So I have a simple system. I have a reservoir on the top of a hill, pipeline running down, then I have a control valve, and then I have a tank. And this tank gets filled. And I want to close the valve when the tank is full at 8 meters. Yeah, that's what I want to do. So let's jump to the Wanda model. I have here the Wanda model. So I have here my reservoir at the head of 20 meters. It's a constant reservoir head. And it starts at 20 meters and then it runs down to 0 meters. And then I have my tank. The tank is filled, starts at 1 meters. And of course, at some time then it's filled to 8 meters. Yeah, starts to fill. So if I run the simulation without closing the valve, we'll see fluid level is rising. See also that it is not a constant discharge. Look at the discharge. Discharge, not the head. You see the discharge, of course, also decreasing over time. It's logical, of course, because the head in the tank increases for your hydraulic head, or your pipeline decreases, so the discharge to your pipeline will decrease. So now we want to basically close the valve when it reaches 8 meters. I will show you how to build this control system. First of all, I need to measure something. I want to measure the fluid level in the tank. And this sensor is now measuring the fluid level. Then I need to have a comparison. So I'm going to use a condition, simple condition, and just connect it to the sensor. So fluid level is put into the condition. I'm going to say to the condition, okay, if it needs to be true when greater than 8 meters, at that point, basically condition becomes true. And I'm going to use, this time I'm going to use a multi-stage pattern. Basically, it's a component which you can use to model a multi-stage closure of a valve. And now I'm going to use just one single stage. I have two inputs. I have a logical input, which is basically the trigger for it to start following the pattern. I also need to give the initial position. The easiest way to do that is to measure that from the valve. And in the end, I need to relay this signal back to the valve. A little bit more nicer. So now I only need to fill in these values. So I need to say how fast can it close. Now let's start with 10% per second. And it goes to 0. Oh, now we have built our control system. Now we need to test it. So let's run the model. So let's see what's happening. So we're measuring here the fluid level. And at 8 meters, now it stops. Something is happening. That looks okay. So happening here. See, okay, this one is triggered. True signal, and then let's see. This one is doing basically at that moment the valve is closed. It looks very fast, but if you look at the time axis, it's from 0 to 360 seconds to 1 hour. So if we zoom in a little bit more, you can see it closes now in about 4 seconds. It'll be too fast, but it's not instantaneous anyhow. And then if you look at the fluid level in the tank, we already just saw it, it's still okay. Now it's a little bit above 8. If you don't want that, of course, you need to trigger it a little bit early. Then you can also let the valve close a little bit slower. Of course, you can play around with that. So we could make this valve much slower. So that's the effect there. A little bit slower. Let's look here. Still, it's not less than 5 centimeters above this one, and we need to make it really, really slow. And that's, of course, the nice thing about integrating this control simulation. As you can see, I can easily test this without jeopardizing the real system. And where do you have good inputs then? Now you can see, okay, now I really have an overshoot. So if I have that, and I would say, okay, start to close here, but at 20 meters, what is it? Oh, 20 centimeters overshoot. So I should start to close a little bit earlier. So let's do that. So a little bit overshoot, so I can start it a little bit. But as you can see, then you can easily, okay, tweak this to get it to the proper level, but that you don't get any overshoots. Also, the closure is much slower, as you can see. So you see immediately how, or even for the simple system, it can be very helpful, because now you know, okay, I close this valve this slow, and I need to start a little bit sooner, and I can determine it when to close. And this is especially helpful, for example, also if you have a system where you're going to look at, if you're closing a valve, you need to trip a pump at a certain pressure level to keep the pressure within your pipeline within certain limits. It can be very helpful to easily manipulate this, and not, because of course you can also do it by closing the valve, but then I need to change this valve closure, timing, and so on. And this is just automatic. I even can say, okay, I have a different discharge, so it starts at a higher discharge. I don't need to change anything because it automatically picks up the correct valve position. You can do the same simulation. You check, okay, I have much more overshoot because I start much higher, so maybe I need to close my valve faster. But it can all easily run the different scenarios, have insights in what's happening in your system. And then I have one other example on control. Going back to the district heating system. Again, we have one source. The model a little bit different orientation. Still, we have the pumps, the check valve, then we have the heat input. And then here, we have a little bit different component. This is basically where you can set a certain demand pattern for the heat. That will be subtracted from the fluid. Then I have a control valve. And basically what I want to do is I want to keep the return temperature. I want to keep it basically constant. And of course, this one is following a pattern. And here you see an example of this pattern. So it starts at about, say, 12 o'clock in the night, and it drops to, well, not completely to zero, but to a low value. And then in the morning, it rises again, and goes down and goes up again. Basically, this one is varying its heat demand in time. And of course, with the constant flow rate, then temperature here would change. What we do is this valve, we want to control it such a way that try to keep the temperature here constant. To do that, what we need to do is we're going to use PID controller for that. I already prepared the model for this. Let's have a look at how it works. So first, of course, we start with a sensor which measures temperature, because that's a controlled quantity we want to control. Then we have our control block, the PID controller. The PID controller output is connected back to the valve because it's an actuated value. It's coming into the valve so that the valve can change its position in time. And you can also see we measure the valve position and put it in here. That's just to initialize the PID controller to a correct value. And then we need to give it some input. We have an initial value. You say something about how accurate the recording is. You need to say, okay, how often do you calculate a new value? Now put it the same as simulation time. And then we need to set some values for the PNI, because we are using a proportional and integrating part. We have a proportional part. We have an integration time constant. And then we need to say something about the bounds and how fast the valve position can change. And of course, the interesting part is that, okay, if we can run this, then we can also start playing around with it. And of course, this one model I have already run. So let's see what's happening. So first of all, if you look at the heat demand, see it changing in time, following the pattern. So we're delivering the heat we want. And of course, that means that here, temperature will fluctuate over time. Since I'm changing now already the valve position, then what I can do, I can just remove that and run it without and see more effect. So what we see is, because now just basically have a system with constant flow rate, valve is kept at the same position, pump is also running at the same speed, and then we are changing the demand. And then what will happen, of course, we decrease the demand first. So let's demand pattern here. So demand is decreased, so the temperature rises, because then you take less heat out, so the temperature stays higher. And then we increase the demand, so the temperature will drop. It's a little bit constant. See, it's just following the pattern in reciprocal value, so to say. So if you don't control it, it will change over time. So that's why you want to put this control in there. Okay. That's nice. Let's see what's happening. So we have this control system, and now if you look at this, the temperature, you have some peaks, but at the end it's going back to the value you want. Okay. So what happens if we going to increase the gain? Basically, okay, make it more aggressive. Let's turn this model on. So I get all kinds of errors. So let's see what's happening. Let's have a look at this valve position. What's happening here? Basically, every time step, the valve is changing from position from 30 to 80, back and forth. It's very aggressive. So, if you look at the return temperature here, see also, so it's, okay, it's below my bound. Okay, I need to open up. Open up, okay. It's above, okay, and back and forth, and just switching back and forth. It's much too aggressive because its gain is much too high. It's very aggressively stirring towards the value, but by doing so, it's giving a huge overshoot every time step. And then, oh, it's okay, I'm on the negative error, so I need to go the other way. And then, oh, go back the other way, go back the other way, go back the other way. Like if you're you would have a car with cruise control, and you set it to 100 kilometers per hour, and first it accelerates to 120, then it brakes to 80, and then back to 120, and that's not good. That's basically what's happening here. And it becomes so unstable that the simulation becomes unstable. That's why I it's used it. So this you don't want to do. This is much too fast. Okay. So let's have a look. Okay, instead of increasing the gain, making it faster, okay, let's make it less aggressive. Make it the gain smaller. Let's have a look what's happening there. We're going to look at the valve position. It looks much better. It's not that aggressive. It's nicely following a certain pattern or is doing something. Okay, that's good. Let's have a look at the temperature. It's following the temperature. If we look at that, what's happening, temperature is going up to almost 90 degrees and dropping to 45 degrees. We're going to compare it with previous results. You see, oh, there's much more overshoot. So because it comes much more slower, you have it way more down. So it's not like, okay, you have an error, and then, okay, a small spark I can take up and steer towards the value. So it comes much too slow. Yeah, so saying, okay, what we just saw, okay, make it just very small. That's not the solution. You need to find optimal. And from control theory, you can actually derive some values, and also with some step response simulations, you can derive a proper value for your initial guess for your gain and integration time constant. But it's a little bit too far for this short course to go into depth. And final thing, which you can also say, okay, let's make my integration time constant much slower. Because it was 10 seconds, changed here to 500 seconds. Again, we see a slow moving valve. Again, if you look at the temperature, again, it looks way overshooting and undershooting, but that's not what you want. So basically, my first guess is the correct one. Of course, this was not my first guess. I also played around a little bit with this to get this working. But as you can see, based on this, you can already, using the PID controller here in Wanda, combining this control simulation, you can already have an estimate of your proper settings for your PID, which you can use also in the field. Of course, one important thing to take into account is the formulas which are behind it. How have we defined the gain and integration time constant? Because those are needed to translate it back to values which you can program in your PLC. And therefore, you can look in the manual page where it's described how we have implemented it. So, and I just mentioned PLC, and let's come to one final important topic, what we call virtual commissioning. Because yes, we have a nice control system, but how do we know that people who build the control system actually build it according to specs and that it will work? And for that, you could test the PLC with a digital twin of the system. And for the digital twin, you can use Wanda. Because Wanda can be coupled to a PLC to test the PLC. Basically, Wanda is then not modeling the control system, but Wanda is then modeling the hydraulics, pumps, the valves, and the control system is just doing the controls. So basically, the sensor measurements come from Wanda. So where there's a flow meter, there you put in Wanda sensor to measure the flow. Where there's a pressure sensor, you put in Wanda pressure sensor. And those are transferred to the PLC. The PLC can do its calculations, and then it will give back the actuated value. So what's pump speed, what is the valve position, and Wanda can use that, run a time step, give values back. So you can then test different scenarios. So for example, for a wastewater system, it's quite useful because then you don't have to wait until you have enough water to test all the conditions and then start testing it in the real system. No, you can test it in one day with the laptop with hydraulic model coupled to PLC, and you can do the tests. And to show that this works, I'm going to show one example case where I've we have been doing this, and this is on this structure. This is the Maasland barrier in the Netherlands, which is one of the primary flood protection for the cities of Rotterdam, the port of Rotterdam and Dordrecht. And it's a floating barrier. And this floating barrier, as you can see on the picture, normally if it's open on the side, then it floats in. And then this white wall consists of reservoirs where you have valves and pumps. What happens then, to sink it, they open the valves and it starts to sink until it reaches the bottom. And if they want to float it, there are pumps, they can pump the water out and then it can rise again. And this has been built in the 80s, and now they need to upgrade the control system. But as you can imagine, you just don't want to put a new control system in this primary flood protection system of the Netherlands, because if it doesn't work, we have a big problem. So we need to build a system to test the new control system to ensure, okay, it works as it should. We call it an acceptance environment that needs to be built. Yeah, and why this new control system was needed is because there was one condition where at a certain point it could be that due to certain wave conditions that the water level on the river side becomes a little bit higher than the water level at the seawater level, and that gives a force in the direction, of course, into the sea, which is something the barrier cannot withstand. It can hold if the seawater level is higher than the river level, then just pushed into, and then it can stand, but the other way not. So what they need to do is at that moment when that comes, they want to raise the barrier just a little bit so that it equalizes the water between the river level and the seawater level side. And that was something new added, and that needed to be tested, okay, how that worked. Normally, if you have hydraulic software like Wanda, you have your user interface, you create an input file, you have the calculation core, which is called, does it calculation, gives you an output file, and in the user interface you can read it, you can adjust your inputs, and that's how you normally would work. But for now, for this virtual commission, what we need to do, we have the calculation, we have basically a test environment. In this case, it was an OPC server, but it can also be a PLC. PLC and OPC server to communicate again with the control system. From there, we get the valve and the pump actions, which goes to the test adapter, which goes into the calculation core, and that gives back pressures, flow rates, water levels, or in this case also the water level in all the compartments, but also how much it has is below water level, and if it is tilted or not, how much it is tilted. So a couple of angles it also passes back. That's what needed. And to add more complexity, the test environment consists of 6 full server racks. There are 6 servers. One was for Deltaris for the test suite, so we'll talk a little bit about which one we had. There were 18 soft controllers on 4 different servers. There were 9 physical PLCs. So, and they also needed to do the input-output for the control system of the barrier. And there were over 360 plus signals which needed to be transferred. Okay, and this is a very special case, but you should remember that also for, if you have a simple wastewater pumping system, for example, there are a lot of signals which you need to take into account to ensure that the PLC can do its work, because it is not only the pressure and the flow, it also needs, for example, maybe temperature and stuff like that, which you might not get from Wanda, so you need to think about that before doing that. Also in this case, we need to think about all the signals. Okay, which signals are coming from the test adapters and which signals we need to do some tricks to mimic them so that the control system can actually do the tests. So what we have built then, we have 2 test suites. One was the model of the water levels. It was based on the Deltares model SOBEC. There we have a model of basically entire rivers of the Rhine and the Meuse to take that into account. And it can also simulate the hydrodynamic interaction of the barrier with what's happening in the rivers. So of course, if the barrier is down, water levels at the river will rise because still water is coming in, but it cannot get out. But those kind of things that the SOBEC model can calculate. Next to that, we use WANDA. For WANDA, WANDA modeled all the reservoirs, the valves, and the pumps. You see here on the side, see a screenshot of the WANDA model. You see, okay, you have the valves for you want to sink it. You have the pump to empty it again. And in the center, you have the reservoir. It can be filled or empty. You also need to make a special component to know, okay, to determine where the entire wall, the barrier was. We need to do that based on a torque balance. And we need to look at the rotational angle. So the rotational angle going down and also the rotational angle on the side. To be able to calculate that. So we built this complete model and then we put that in this server rack on a virtual node to run and then couple it to the OCP server. And then also we need to balance the time steps because this whole process of floating the barrier into it and let it sink is not a process of an hour, that is of hours. It takes about, I think, a total of 4 hours to float it, get it into, and then let it sink. But what we have seen is that WANDA can be coupled to PLC for testing, and rest assured, we also done it for much simpler systems. And also, not only Deltares has done it, also other companies in the Netherlands also have already done this. But before you want to do that, you need to have a good agreement of your model. You just have to trust your model because you're going to use your model to validate PLC. But if your model is crap, your model is not good, then of course you cannot test it. Yeah, you can test it, but then we'll say it's wrong, but that's not the real case. So you need to have validation, good agreement with measurements to ensure, okay, we know what the model is doing. What also helped you in the problem in this case is that at some point also the operators of the barrier started playing with the model to see, okay, what's possible and not. That also gives them trust. Okay, you start to get trust in the model. That also helped. And at the end, this virtual commissioning can save a lot of time and also reduce errors in the control system. That's not only for this case, for all the cases. And of course, here it's a really special case because it was on primary flood protection, so it was really needed to do it a little bit different. But doing it in this way, you could ensure, okay, yes, it works, and easy to find. There were different scenarios, really test if the new control system is up to standard. So, talked a lot. Hope was useful for you. So, main takeaways I want to give to you is, okay, first of all, check your boundary conditions. Ensure know what you're doing, because it's essential for getting proper results we can trust. Also showed you that control system is important to model. It can help you really get insight in the operation control of your system and to verify that and improve that. And last, I gave you an example of how WANDA can be used to couple, to test PLCs, to test control systems. It's also really helpful because basically, if you have done a study with WANDA, then you have the model already, then it's an easy step to do this testing. And maybe good, thank you for your attention. Good to know that as Deltares, we also give some courses you can see here. So we have some online search course starting already in 10th of April. So if you're interested, there's still a couple of seats left, so you have to be quick on that one. In the fall, we have some courses, some basic courses and advanced courses in Wanda. And maybe most importantly, next year, in April, we will be hosting the 15th International Conference on Pressure Searches. So you're all more than welcome to come there. The deadline for abstracts is already passed, but if you think, oh, I really have something which is really interesting for this conference, please contact me so that we can discuss and see what's possible. And finally, I talked a lot about Wanda, and it's of course a software which from Deltares. It's commercially available. You can find the information on that on intranet. But of course, you can always start with a trial. If you go to the website, put it here. You can also search on Google Wanda Deltares. When you come to this website, there's a big button, request for a trial. Just send an email and then you get a trial license where you can test Wanda for a month to see if it fits your need. So thank you very much for your attention. And I'm going to give the word back to, I think, David.
Okay, thank you very much, Sam, for your very complete presentation and insightful demonstration with Wanda, and also for the interesting examples you showed. I found especially interesting the example on district heating, which, as you mentioned, they are more and more important infrastructure that we need to understand and describe well. Okay, so we have quite a number of questions in the Q&A. Let me go through the first question, which it's actually two questions. What is Deltares' business model with Wanda? Do you commercialize it through a license, or is it free software? And maybe the second question is, can you give an overview of Wanda community of users?
Yeah, I can answer that. So it's not free software. So yeah, it's commercially available, so you have to buy a license. But it is a perpetual license. So if you buy the license, you can basically use it as long as you like. And next to that, we sell a subscription so that you're entitled to support and new updates. But I should say that if you're a researcher at a university or a PhD student and you have an interesting case to work with Wanda, please contact us, because then we can discuss on if you can use the software maybe for free even. That's always possible for us because we are a research institute and we want to support also research and to collaborate on that. So yeah, please contact us on that. And for the community of users, yeah, it's a very wide range. In the Netherlands, we have, for example, the water board, who are responsible for the wastewater transport. They are active users, but also drinking water companies, but also engineering firms. So it's really a wide range of people who are using Wanda.
Okay, thank you. And the second question is actually a question that I also had, which is, thanks for the interesting presentation. I would like to know if one can import the APANET files in Wanda.
Yeah, you can import APANET files into Wanda. And then, as I just showed, then basically you get a choice to use these tabs, because in APANET, of course, you have this the demand nodes. And those can be automatically changed into these tabs, so that you can do the transient modeling you want to.
Okay, thanks. Next question. Okay, it's you already answered this question, which is not free software, but it can be free for academic institutions. And the following question: what do you think is the best method for modeling the boundary between a pressurized force main and a gravity sewer? How do you account for the introduction of air into the force main?
Yeah. So if you have going from pressurized to gravity flow, if you know where the boundary lies, then it's easy to, of course, to model it. In Wanda, we also have a free surface pipe model, so then you can model that. If you have the interface is moving, then it becomes much more difficult. Then also Wanda doesn't have a component where you can go from free surface to complete pressurized pipeline. So that's not possible to do. If you need to account for air into the force main, again, Wanda is That's a simple software, but it's just one phase, one fluid, so we don't take introduction of air into account. But we do have air valve components where you can, where you get air inlet basically after a pump trip, but then the air is not transported into the pipeline. You can take into account the drop of water level in your pipeline, but not transport of air through your pipeline, because that becomes very much complicated, because then you need to take all the different flow regimes which are possible into account. You basically going to build a multi-phase flow simulator. We're still interested in looking into that, but that's becomes very complicated then.
Okay, the next question is from Alex Balzarini, which is actually a similar question as Elena Ramos had in the chat box. Can Wanda also effectively model transient flow phenomena in large hydropower plants and or pump storage systems under various operating conditions? Or is it primarily designed for water distribution systems rather than large-scale hydropower applications?
No, but Wanda can cover all systems. There's no limit on that. So also large hydropower systems is quite possible. So maybe to give an example, you can simply, the models I showed you were very short pipelines, like 5 kilometers or so. But yeah, of course, I chose that for the easy of simulation. But I've myself worked, for example, also on large water transmission schemes, which you have DN 1.6 meter pipelines for 100 kilometers. It becomes already much larger, but you can even go larger if you want. There's basically not a limit on that. But you can also go much smaller scale. In the past, colleagues of mine have even modeled the landing gear of a helicopter during an emergency landing. You have some hydraulic cylinders and some pressure transient occurring there. That has also been modeled with Wanda. And then you have the system becomes much smaller. So Wanda can be applied to very small size systems, but also very large size systems. So indeed also hydropower systems. Wanda can also, and Wanda also has a turbine component, which you can use to model a turbine also.
And to complete this question, Elena Ramos had the question that if Wanda can simulate different types of turbines.
That I'm not that familiar with the type of turbines, but what I can show you. The liquid turbine. So we have the turbine here. I don't know if it's. You're basically using the unit curves of the turbine, but I'm not sure if you can indeed easily model different types of turbines with them. Because I'm not using that much. I'm more in the water transmission schemes and in the system with turbines. So I can get back to that and ask my colleague about that because he knows a lot more on that.
Okay. So yeah, I guess it's based on a standard Francis turbine.
Yeah.
And
So.
okay. Great. Next question: how is temperature dependency of cavitation considered in Wanda?
That I can also show because I have Wanda open. So we have here in the fluid window. You have here a table of the temperature and the different fluid properties. And this one a little bit to the side. And here, one of them is the vapor pressure. So basically, the vapor pressure is temperature dependent. So that's how we can take that into account. At the different temperatures, you have a different vapor pressures or a different temperature it starts to cavitate.
Okay, so vapor pressure is considered as a fluid property, temperature dependent, and this is how it's considered cavitation during, for instance, in the example you gave concerning heating district modeling, right?
Yeah, indeed. Yeah.
And maybe now a question came up to my mind related to this one, because not only the fluid properties are temperature dependent, but also the pipe wall properties, the material of the pipe wall, like the Young modulus of elasticity, and this may affect the wave celerity. Is this considered in Wanda?
At the moment, of course, what you can do is you can, this one is not set to Waterhammer, you can set the Young's modulus, so there you can choose, okay, I know which temperature this pipe is going to be, and then you can set it based on that. So the user can set it him or herself. Because basically during transients, of course, the temperature will not change that much, because the temperature change is transported with the flow velocity, so that's much slower, of course, than pressure transients. So you can assume that temperature will remain constant. So that's how you can introduce it. And this paper I refer to is also looking into this, okay, well, we have the bulk models, but also you need the pipe wall properties which change due to temperature change. What's the effect on the wave speed?
Okay, very interesting. I think you already answered the next question, which is if you can also simulate hydropower systems. Then also Pashupati Kumar is asking, how is this better, MATLAB Simulink or ANSYS Fluent? Well, they are different modeling approaches, right?
Yeah, Fluent is 3D CFD software, and Wanda is one-day CFD basically. It is one-day pipeline hydraulic software, so really focusing on the pipeline. While Fluent is much more broader, you can basically do any fluid transient, but that makes it also much slower, because there you would have hours or days simulation time, while Wanda is normally seconds to minutes simulation time, so time to do simulation. MATLAB Simulink is a completely different package to, and there, of course, you can also build a Waterhammer solver in there. But here we just said, okay, we just focus on that. Gives us much more freedom to develop.
Okay, the next participant is asking what information required by Wanda to represent source protection devices, for instance, air valves, caused by the manufacturers, or does it have a database of typical devices already included?
No, we don't have a database of data included, so that is not readily available. But as usual, you can create your own database. You have the possibility of to store properties of components, and we use them. And for some, we have some examples in there, but yeah, those is very limited example database. And if we look at search devices, for example, if you have an air valve, basically we have two ways to define it. You can define it with setting the area and a discharge coefficient that determines the curve, or you have another possibility where you define a characteristic, which should of course be supplied by the manufacturer based on differential pressure you get in certain discharge, so that the user can, you can set it yourself. But I said you can also, if you have a lot of data, you can already create some property template files which you can load into the software. And maybe in future that's something to look into to see, okay, can we get from different manufacturers, can we get data? But for us, the difficulty in there is that as Daltaris, we are an independent research institute, so we don't want to favor one manufacturer over another. And that might, if you only get from one manufacturer data, then that might be become a problem. So we don't want to be tread carefully in that.
Yeah, and it's also a good way to engage manufacturers to provide the right data, right? Okay, and the last question, actually, it's a good question to finish. Anil Kutu, I guess he would like to join the course being organized by the Altares. So she's wondering about the fees for the online course.
I don't know by heart. Let me check if I can find it. In a second. You can just find it if you go search on Daltaris course on.
Maybe you can provide the link later in when answering his typing an answer directly in the Q&A.
Yeah, I can put it in the Q&A. Yeah, I will do that. Yeah, that's good. That's
okay.
good.
Great. So I don't see any more questions coming up. Yeah, sorry. Kusai. Kusai Khaled, can you use Wanda for transient-based leak detection in water distribution networks, or would it be an interesting use case?
That would be a very interesting use case. We ourselves also looking into that. A colleague of mine has been doing measurements in a single pipeline, and the use case for what he's doing is at the end is indeed transient-based leak detection. But what we are looking into basically is the unsteady friction phenomena. And what he has been doing is PFE measurements for changing flow, so transient flow. So he is closing a valve and then doing PFE measurements to see how does the flow pattern change over time, to give answer to improve the unsteady friction models. Because I think if you want to be looking these kind of details, then that detail needs to be included. So that's an important step in there. So, but yes, it's a very interesting use case for us. So if you have ideas on that, please contact us and we can discuss. We're also always open to collaborate on research, together write research proposals. Of course, we have our software, but we also have felt that there are some nice facilities which can be very useful because they are just a scale bigger than what the university has. So that makes it also more applicable to real life situations.
And maybe a question related to this. Can you use Wanda in inverse mode for inverse analysis?
Or in reverse mode? No, that's not implemented yet.
Okay. But you can launch Wanda from outside, no? From a Python MATLAB interface?
You can run Wanda from Python, and you can even just also run it on a time step basis. So run one time step, change some values, run next time step, get some values, change some values. So that's
so you can always develop your algorithm and then launch Wanda from your own algorithm, no? And okay. Great. Okay, so now, I don't see any more questions. So I think we can finish the discussion here. Thank you very much, Sam, for your very complete presentation and nice discussion. I see in the program that the next talk it's at 3 p.m. Central European time, which means exactly in 15 minutes. So let me suggest to do this short break, 15 minutes, and then we can start afterwards. See you in a bit. Thank you. Good afternoon and good morning, everyone. It's now time to move to the third and last session of today. For the purpose, I would like to introduce Dr. Christophe Nicolet, who is the Managing Director and co-founder of Power Vision Engineering, an external lecturer at the EPFL École Polytechnique Fédérale de Lausanne, where he obtained his PhD in 2007 in the topic of hydroelectric transients modeling. And Simpson, the software he will be presenting today, is the result of this and a long-standing development, more than 20 years, from Power Vision Engineering. I hope you enjoy his talk. And Christophe, the screen is yours. Thank you.
Great. Thank you very much, David, for your kind introduction. So good afternoon, everyone. Good evening or good morning, depending where you are. I will be sharing my screen. I hope you can all see my screen now.
Yes, we can see it.
Perfect, thank you. So it's my pleasure to present you the Simpson simulation software and some examples of application and recent developments. So basically, I will shortly introduce our company, Power Vision Engineering, and then I will give you an overview of the Simpson simulation software and the modeling of some key hydraulic component. And then I will show some example of hydroelectric models related to variable speed reversible Francis pump turbine and control performance and their possible contribution, then an example with a possible contribution to grid stability. And finally, I will provide a showcase about the Gouveia pump storage power plant, which is located in north of Portugal. And I will show you some work done about the transient analysis during the design phase, and also some recent results from the commissioning of the plant, where we have been able to use a digital twin to follow the transient test performance site. And I will finish with an outlook on the general software. So Power Vision Engineering is a spin-off from EPFL, founded back in 2007 at the end of my PhD thesis, as David mentioned. And we are located next to Lausanne, and we have a strong collaboration with the EPFL. We have at the moment 9 employees, 6 holding PhD degree, with expertise in the field of hydraulic, mechanical, and electrical engineering. And we have a special agreement with the EPFL, which is still the owner of the software Simpson, but we are the exclusive distributor of the software. We're also in charge of the training seminar and in charge of the support and maintenance of the software. But actually, we're also providing engineering services using the software. So we do basically transient calculations with the Simpson software. And we do also more and more system stability studies, including the power network. And we do also some CFD computation. So the Simpson simulation software enables to model hydroelectric power plant, let's say from water to wire, including all the different components, the upper reservoir, the headrace tunnels, the surge tanks, the penstock, the valves, the different types of turbine, the rotating inertia, but also generators, transformer, transmission line, and grid models. And you can include the corresponding control system the turbine speed governor, and also the voltage regulator on the generator side. So it allows to include in the same environment hydraulic system, rotating inertia, electrical installation, and control devices. I'm starting to show you an overview of the electrical library because originally the software was developed for electrical application under the supervision of Professor Simon at EPFL in strong collaboration with ABB at that time. So they have developed the software to simulate transient behavior of electrical machines, including all types of motor generators, combined with all types of three phases component, any kind of converter, and all related control blocks. At that time, of course, they also perform validation of the software on the electrical side. Here you have just an example of application with a rather complex frequency converter used to drive an induction motor, and you have comparison between the Simpson simulation results with the measurements performed in a factory of ABB. You can see that there is rather good agreement. Later on, we have developed the hydraulic library of Simpson, including all key hydraulic components you may find in hydropower plant, including, of course, pressurized pipe, the different types of surge tank, pressurized surge tank air vessels, valves, surge shaft, but very important is it includes also model of all type of hydraulic machines, including Francis turbine and reversible pump turbine, Pelton turbine, Kaplan and Bulb turbine, propeller turbine, and also pumps. And more recently, we have also included models of free surface flow in open channels. Since hydropower combines very well with new renewable energies, we have also implemented models of wind turbines, of tidal turbines, of PV, and of converters. And we have a wide bunch of IEEE excitation system model and power system stabilizer. Regarding the models of hydraulic component is based, of course, on a momentum and continuity equation, which have been shown in details yesterday. And basically, applying the common simplification, we end up with this system of partial differential equation set. And interesting enough, you can see that this system of equation is very much analog to the system of equation you can derive for modeling the propagation of voltage in transmission line, so-called telegraphist equation set. And to the head in hydraulic correspond, of course, the voltage in electricity, and to the current correspond the discharge. Following this approach, you can identify an hydraulic capacitance which account for storage effect related to the fluid compressibility, but also related to the pipe wall deformation. You can identify an hydraulic resistance, which account for the friction losses, and you can identify an hydraulic capacitance, which account for inertia effect of the water in movement. So basically, it means that we can model an element of pipe with such electrical equivalent scheme with a T-shape built of 2 half inductances, 2 half resistance, and 1 capacitance. Viscoelastic phenomena could also be accounted for with this viscoelastic resistance. Basically, this electrical equivalent scheme is reflecting the numerical scheme that is used to solve the partial differential equation set, which is based on finite difference method, where we have used a centered scheme and a lax scheme to solve this differential equation set. And we end up with a set of differential equation which has the great advantage of being capable to be represented with these electrical equivalence schemes. The reason why we have used this electrical analogy was quite obvious, because the software originally was developed for electrical application. Then, of course, we benefited directly from all the system equation automatic addition that was implemented for electrical system and the full modularity. Moreover, it means that the hydraulic equations are solved together at the same time with the electrical equation, mechanical equation, and control equation. So basically, we have only one set of differential equation set, which are all solved with the same integration time step, which ensures that we are properly taking into account all the interaction between hydraulic and electrical component. Here you have an overview of the graphical user interface, where basically you can build up the model of your power plant. Here's an example with a pump storage power plant, including a variable speed doubly fed induction machine with the corresponding converter and associated control. And then Simpson will build the set of ordinary differential equation set using Kirchhoff laws, and the full set of equation will be integrated over time using Runge-Kutta fourth order. And then we can, of course, display the simulation results of pressure, discharge, voltage, current, torques, and so on over time. So we have seen that the model of an element of pipe is composed by this electrical equivalence scheme. So when we are modeling a full pipe, of course, we need to put several times in series this electrical equivalence scheme, which basically correspond to spatial discretization. And this spatial discretization has to fulfill the CFL criteria. And then the integration time step has to be adapted accordingly to the spatial discretization. Then the model of a valve corresponds basically to a variable resistance, which value is changing as function of the valve opening. So it's basically a variable resistance. Regarding model of surge tanks, it mostly corresponds to the capacitance, and the capacitance account for the storage capacity of the surge tank. But of course, there are singular head losses at the inlet of the surge tank. These head losses are modeled with a resistance, and the value of the resistance can typically changes depending on the flow direction. Quite important is in case the surge tank is featuring narrow diameter, then the inertia effect of the water becomes very important and cannot be neglected anymore. And then it means in the model of the surge tank, then we have to account for an additional inductance, which becomes a nonlinear terms, since the water level inside the shaft is evolving over time. But this inductance is modeling basically the inertia effect of the water inside the surge tank. And this inertia effect becomes more important in cases where we have fast hydraulic transients. So typically, systems subject to pump transients or to pump turbine transients, where discharge may vary very quickly over time. In these particular cases, we need to pay a careful attention to model properly the inertia of the water inside the surge tank, which can be done with such kind of models. Then, of course, very important are the hydraulic machines. In Simpson, we can include models of Francis turbine, which are based on the four quadrant, or for Francis turbine, it's more like two quadrant characteristics, where we input the data as a text file, let's say, and we provide the discharge curve, the unit discharge curve Q11 as function of N11 for different guide vein opening, together with the torque curve, where we provide the value of T11 as function of N11 for, again, different guide vein opening. Of course, nowadays we are more using the quantity NED, QED, and TED, which are non-dimensional according to the IEC standards. There is quite a significant difference between transient behavior of Francis turbine and Francis pump turbine. It has been mentioned by Professor Cheng in the first presentation today. Pump turbines are subject to the so-called S-shaped characteristics between the turbine quadrant down to the reverse pumping quadrant. And this S-shaped characteristics is revealing the unstable behavior of pump turbine when they are going to run away under transient conditions. And this S-shape has a huge impact on the hydraulic transient behavior of the waterway and needs to be accounted very properly into the transient calculations. So this is why it's very important to be capable to go throughout the S-shape without any issue. And to do so, we are using the so-called Suter polar transformation, which ensure proper handling of this S-shaped characteristic. Regarding the equivalent scheme of Francis turbine or pump turbine, basically it's a pressure source which is driven by the discharge characteristic out of Q11 as function of N11, provided we know the guide vein opening, the discharge, and rotational speed. We can compute the head, which is directly driving the pressure source, and out of the torque characteristic, we can derive the torque for the corresponding hydraulic condition, which is used then to compute the time evolution of the rotational speed, taking into account the inertia of the rotating masses. And also important is we can account for the inertia of the water, which is inside the hydraulic turbine through an hydraulic inductance. Then we could also take into account models of Pelton turbines. And from the hydraulic perspective, Pelton turbines are nothing else than, let's say, a valve. So the injector discharge characteristic is handled with a Q11 curve as function of the inject needle position. And then to account for the transient rotational speed of the Pelton turbine, we need to input also the torque characteristic of the Pelton turbine, where we have again the torque unit coefficient T11 as function of the rotational speed, unit rotational speed N11 for different injector opening. Basically, in the model of Pelton turbine, each injector can be driven independently from each others, so that we can really replicate all transient sequence which may occur in the lifetime of a Pelton turbine. Also important for Pelton turbine is the ability to account for deflectors. Actually, we are taking into account deflectors effect through what we have called the deflection coefficient, which is basically the ratio between the discharge, which really goes to the runner and contributes to the torque, divided by the discharge which leave out the injector. So when this deflection coefficient is equal to 1, all the discharge goes to the runner and contribute to torque, and when the deflection coefficient is equal to 0, basically all the flow is deviated and does not contribute anymore to the torque. This modeling approach enables to account for any kind of deflector, would it be deviating the jet or cutting the jet. Then regarding Kaplan turbine, of course, the shape of the discharge and torque characteristic of Kaplan turbine are quite different from the one of Francis turbine. But basically, the model is handled the same way, except the fact that we have, of course, one more parameter, which is the blade angle of the runner. So we do not need only one turbine characteristic, but we need one per blade angle that is measured from model test. So we need a couple of turbine characteristic for different blade angle, and then we are interpolating between different blade angle so that we can handle properly doubly regulated machine, where the guide vane can be driven independently from the blade runner blade position. Of course, as it is the case for any software, when the models are established, we need to carefully validate the software. First, of course, against some academic test cases available, then against different simulation software. But at some point, it's very important also to validate against measurements. And here I will just illustrate a couple of examples of validation we have made between simulation from Simpson and site measurements. The first example is dealing with a Francis pump turbine, which is a variable speed machine, which is installed in the Avce power plant located in Slovenia. It's an 180 megawatts unit operated on the significantly high head, 520 meters high, and the nominal rotational speed is 600 RPM, which can be adjusted plus minus 4% with a doubly fed induction motor generator. Here you have an overview of the waterway with the upper reservoir on top of the hill. You have a headrest tunnel, surge tank, a penstock, and then the reversible pump turbine and let's say the tailways tunnel connecting to the lower reservoir. You have on the right hand side here comparison between site measurements in black and simulation results in color for two cases. The case of emergency shutdown in turbine mode, where we have the comparison of time evolution of the pressure in the spiral case in blue, comparison of the time evolution of the rotational speed, and the imposed three-slope closing law that is imposed on the guide vane opening. You have similar comparison in case of pump emergency shutdown, where again you have comparison of the time evolution of the rotational speed and the pressure in the spiral case. And as you can see, there is a perfect match between site measurements and simulation results, which shows that we are handling properly also the S-shaped characteristic of the pump turbine. The second case of validation is related to a Francis turbine power plant of Hauterive, located in Switzerland. This power plant is equipped with 4 Francis turbines with a total installed capacity of 75 megawatts, operated under a maximum gross head of 107 meters of water column, and each unit has a nominal rotational speed of 300 RPM. Interesting enough is this power plant, 3 of the units, the original unit, are equipped with pressure relief valves, and a new unit of 26 megawatts, for which you have a picture here, is replacing 2 old units which were originally also equipped with pressure relief valves. And in this particular case, it was possible to get rid of pressure relief valve on the new unit. You have on the bottom left here a view of the Simpson model with the upper reservoir, the headrest tunnel, the surge tank, the penstock, the manifold, the 4 unit, and you can see that 3 of the units are equipped with this kind of pressure relief valve. And again, you have comparison between measurements and simulation here on the time evolution of the surge tank water level. In case of emergency shutdown of 3 units, there are indeed 2 curves, a red and a blue one, and as you can see, it fits very well. Here you have the comparison between measurements and simulation for the transient behavior of the new unit number 4, which feature 2-slope closing law. It has a significant overspeed, and which we replicate very well with the simulation. And here we have also comparison of the pressure and the inlet of the spiral case with very good agreement. Regarding the transient behavior of Francis unit equipped with pressure relief valve, here we have the example of the unit 2. As you can see, the guide vanes are closed super fast in about 3 seconds. And in the same time, we have opening of the pressure relief valve. And then once it's open, then we have all the time to close it slowly to mitigate the water hammer. The main benefit of using this pressure relief valve is visible here. This unit can avoid significant transient overspeed of the machine. And the time evolution of the pressure is again very well replicated between measurements and simulation. Then here we have the third example of validation, which is related to the Cloison-Dixence power plant located in Switzerland. It's including 3 Pelton turbines. Each one has a nominal power of 423 megawatts, which today remains the world record and is operated also under a world record maximum gross head of 1,883 meters of water column. Here you have an overview of the layout of the power plant with the Grand-Dixence reservoir, the Grand-Dixence dam, and a related reservoir, a 16 kilometers long headrest tunnel, a surge tank, and then a 4-kilometer long penstock, and which feeds the 3 Pelton turbines. You have the corresponding Simpson simulation model on the right-hand side, and you can see that the particular attention was paid to the model of the surge tank, which features some differential effect when the water level reached the upper expansion chamber, differential effect that Professor Schleiss has explained yesterday. And as you can see, we have very good agreement between simulation and measurements of the pressure at the bottom of the penstock. Here, in case of emergency shutdown of 3 units operated at full power of 400 megawatts, so it's emergency shutdown of 1.2 gigawatt. And we have also very good agreement of the time evolution of the water level in the surge tank over the long term. Finally, I would like just to show an example of validation of Kaplan turbine. It is the Lave power plant, also located in Switzerland, equipped with 3 Kaplan turbines of 31 megawatt each, operated under a maximum gross head of 42 meters for a total discharge of 255 cubic meters per second. What is quite particular for Kaplan turbine power plant is the fact that there is a rather long headrest tunnel of 4 kilometers long, which then required quite large surge tank, which has a differential effect for the upper expansion chamber. So there are 2 chambers on the side when the water level reached the top of the main inlet pipe. And then the headrest tunnel split in three to feed three penstock, which feed the three different Kaplan turbine. You have again the corresponding Simpson model with again a particular attention paid to model properly the differential behavior of the surge tank. And as you can see here, we have also very good agreement between measurements and simulation for the time evolution of the rotational speed of the unit, for the pressure at the inlet of the spiral case, and also the water level in the surge tank in case of emergency shutdown of one unit at full power of 30 megawatt. So now we have seen that we can model very properly transient behavior of hydraulic system of hydropower plant. But one of the great advantage of Simpson is the fact that you can combine hydraulic models together with models of electrical machines. And here it's an example of detailed model of a variable speed pump turbine of 320 megawatts, which is driving a doubly fed induction machine where there is a voltage source inverter to feed the rotor. And basically, this power plant features a gross head of 552 meters of water column, and the unit is operated at 450 RPM. And of course, the reversible pump turbine are modeled with 4-quadrant characteristics. Here we have integrated also the model of the turbine governor and the model of the motor generator. And basically, for this application, the motor generator control is taking care of the active power control, while the turbine governor is taking care of the speed control. And in the turbine speed governor is included the speed optimizer, which enables to select the optimal rotational speed as function of the head and power set point in order to maximize the efficiency of the unit. And here we have an example of simulation results in case of active power set point changes. And basically, the set point is changed instantaneously, and the active power simulated in blue can follow extremely quickly the set point and allows to respond in about 0.3 seconds to a 20% load variation. This is possible, of course, only thanks to the fact that it's a variable speed unit, thanks to the so-called flywheel effect. So the difference of power between the original active power set point and the final active power set point, the excess of energy is then stored into, converted into kinetic energy, and results in an transient speed variation of the unit. And then the turbine governor react and control the speed of the unit, which is bring back to the new optimal operating rotational speed, allowing these very fast active power set point changes. And here we have typical response of the pump turbine under load variation. Here is an example of the response of the same unit, but in pumping mode. Again, regarding the control strategy, the motor generator is taking care of the control of the active power. And in this case, we don't need to regulate the speed. The speed is kind of self-controlled through the natural torque characteristic of the pump, but we can adjust the pump guide when opening in order to achieve the best efficiency of the pump unit. And again, here we have simulated a change of active power set point very fast. And you can see that the blue curve, which is the power response of the unit, shows that the unit can respond again in 0.3 seconds to a 20% load variation of the active power. And as a result, again, you have a change of the rotational speed. And this is again this flywheel effect, which enables so fast active power input variation. And here you have the resulting time evolution of the guide vane, which are adjusted in order to maximize basically the efficiency of the unit. And just to show that the simulation results we obtain are realistic, here you have an example of measurements, site measurements, performed by Hitachi back in 1996 at the Okawachi power station, where they have recorded power response of 400 megawatts variable speed pump turbines operated here in pumping mode, and you can see that the power set point can indeed be adjusted super fast, and you have typical transient response in speed and adjustment of the guide vane to maximize efficiency of the unit, which results are very similar to the one we have obtained by Simpson simulation. And in their papers, they are reporting time response in active power of 0.2 seconds to change the power of also around 20%, which is very much in line with the simulation results we have obtained. Then this very fast power response can be used to provide ancillary services to the grid. As you may know, in case there is a significant event on the grid, which would trigger disconnection of some generation capacity, the frequency of the grid would drop. And then to recover the nominal grid frequency back to 50 or 60 hertz, we're using different kind of grid services like frequency containment reserve, FCR, or frequency restoration reserve, FRR, or automatic FRR, AFRR. And then we are using replacement reserve to restore all the AFRR capacity. So these control services are also known as primary, secondary, and tertiary control. And the ability of hydropower to provide such kind of ancillary services was extensively studied in the framework of European project X-Flex Hydro that was finished last year in February. And basically, we have assessed the capacity of different hydropower plants to provide different grid services, which are listed here, where we find back the FCR, frequency containment reserve, the AFRR, the manual FRR, and the replacement reserve. But we have also assessed the capacity of the unit to provide emerging grid services like fast frequency response, FFR, where we expect active power response in less than 2 seconds, but also the ability of the unit to deliver synthetic inertia in case of variable speed units. And we also quantified the synchronous inertia contribution of the different unit. And we assessed also voltage capacity, voltage control capacity, and black start capacity. To do so, we have taken as a reference the grid code, the French grid code established by RTE, and basically we have used it for primary and secondary control. And regarding the specification for fast frequency response, we used the grid code established by NTSOE for Nordic countries. which is shown here. And today, to illustrate the ability of variable speed to deliver this kind of different ancillary services, I will show the case of Frades 2 pump storage power plant, which is located in north of Portugal and equipped with two reversible pump turbines of 400 megawatt each, and equipped with double fed induction machine of 420 MVA. The plant is operated under maximum gross head of 400 meters, 430 meters of water column. And the rotational speed can vary between 350 up to 381 RPM. Here you have an overview of the Simpson simulation model that was elaborated for this power plant, where you have the view of the hydraulic system with the upper reservoir, the headrest tunnel, the surge tank, the upper surge tank, then the penstock, which feeds the two reversible unit, the draft tubes, the tail, the draft tube tunnels, which connect to the downstream surge tank, and then the tail race tunnel. Here we have also integrated the model of the unit controller, which includes, again, power control on the electrical side and speed control on the turbine side, including speed optimizer. And interesting is also the integration of control control loops to provide the different ancillary services. So the set point here, which is provided to the unit controller, includes the contribution from IAHR for secondary control, which is summed up with the contribution of FCR control capability, which is represented here, which respond as function of grid frequency deviation, but also sum up with the contribution of FFR control capability, and together with the synthetic inertia control loop. And all these control set point contribution are summed up together and delivered as a power set point to the motor generator. Now we have some simulation results of the response of this pump storage power plant of Frades 2 for the different types of ancillary services, starting first with the automatic AFRR, automatic frequency restoration reserve. And what is particular here, we have simulated the case where the plant is operated in hydraulic short circuit, where we operate one unit in turbine mode. At the same time, we're operating one unit in pumping mode. So one unit is at 204 megawatts in turbine, while the other unit is at 90 megawatts in pumping mode. That's the magnitudes of the power set point variation, actually, that each of the unit can deliver in 300 seconds. So they are following a ramp of 300 seconds over time and can deliver 200 megawatts and 900 megawatts for the turbine and respectively the pump unit. And here you have the transient behavior of the corresponding pump turbine. Of course, to follow such a slow power set point is not difficult for a variable speed unit. What is more difficult is to respond to primary control, where response time is expected in 30 seconds. And here we have shown that the unit of Frades could respond to frequency deviation with a maximum amplitude of FCR reserve up to 186 megawatt in 30 seconds. So that's almost the half of the nominal power of the unit, which can be delivered in 30 seconds. And here you have the corresponding transient response of the pump turbine in case of frequency drop and power increase, or in case of frequency increase and power set point decrease. You can the beauty of variable speed is the fact that in pumping mode, you can also adjust the input power. So here we have also evaluated the capacity to to contribute to FCR, to primary control in pumping mode. And basically the unit can deliver 45 megawatt plus minus in 30 seconds. And the 45 megawatt plus minus correspond to the full range of active power control of 90 megawatt of the unit. And finally, here you have the example of contribution to the fast frequency response in turbine mode, where the unit can deliver 80 megawatt in 1.3 seconds. So here you have a power set point step, which is performed in 1.3 seconds, and then it has to last for 25 seconds. And then the power set point is getting back to the initial value. And here you have the corresponding transient behavior of the unit. So this fast active power changes is possible thanks again to the flywheel effect of the unit. And finally, actually, we have also simulated the ability to contribute to a black start capacity of the unit. And we have shown that we will be able to achieve a power step of 113 megawatts in case of black start. But this requires special control capability of the unit. This kind of unit is usually operated in grid following mode, but for black start capacity, we would need to have a grid forming control capability. But here again, you have the transient behavior of the pump turbine. Then all these grid services, you can take advantage of it to see what could be the contribution of an hydropower plant, and more specifically a pump storage power plant, to grid stability. So here is just an example of the layout of a test case where we have an hydropower power plant, pump storage power plant with 250 megawatt unit with variable speed motor generator, combined together with a thermal power plant of 1.3 gigawatts nominal power, combined together with a wind farm of 200 megawatts. And here you have a consumer load. And using this kind of model, you can analyze the contribution of hydropower to stabilize the grid frequency and to respond properly to variation, for example, of new renewable like wind power or of PV solar output power variations. So now I would like to follow with the example of Guva's pump storage power plant, which is nominal power of 880 megawatts, and it's located in north of Portugal. And I would like to explain a bit some hydraulic design challenges of this high-head power plant. And I'd like to mention that this work was done in collaboration with Iberdrola, the owner of the plant, and TU Graz University, and more specifically the Institute for Hydraulic Engineering and Water Resources, head at that time by Professor Zenz, with the contribution of Wolfgang Richter. The Guva's pump storage power plant is part of the Tâmega hydropower scheme located in north of Portugal, which includes also two other conventional hydropower plants, Alto Tâmega and Daivos. So that overall it corresponds to an hydropower scheme of 1,160 megawatts installed capacity. This power plant was put in operation back in 2022, but the study started back in 2014. And I would like to show a bit an overview of the different steps achieved during the design phase. So here you have an overview of the hydraulic layout of the plant. As you can see, there is quite a long headrace tunnel of 4.7 kilometers long, at the end of which there is a differential surge tank. This is a Johnson differential surge tank, as the one shown yesterday by Professor Schleiss. Then there is quite a long penstock of 2.2 kilometers long, with a diameter changing from 6 meters at the top to 1.6 meters at the inlet of the different unit, with 2 parallel vertical shafts, which split then in 2 to feed each of the pump turbine units. Then you have a cavern with 4 reversible pump turbine of very high head, 660 meters of water column, with nominal rotational speed of 600 RPM, which leads to very low specific speed unit with NQ of 26. And such a low specific speed unit are subject to very pronounced S shape, which makes the corresponding transient behavior extremely severe. And then on the downstream side, we have 4 draft tube tunnels, which are connected. Each of them is connected directly with through vertical pipe to the downstream surge tank, which includes lower expansion chamber and upper expansion chamber. And then we have a tail race, which is 700 meters long to connect the downstream reservoir. And again, this downstream surge tank has a differential effect on the upper chamber. If we have a look at the overall design process of the surge tank, specifically, a preliminary design was made by Iberdrola to define the layout and define the topology of the surge tanks based on a simplified 1D transient calculation. Then we have been requested to perform some optimization using 1D transient calculation with Simpson, where we have included a realistic 4-quadrant characteristic to account for the S shape of such a low specific speed reversible pump turbine. And then we have done a first optimization of the surge tanks in terms of volume, cross-section area, diameter of the connecting pipe, and so on, for all the different operating conditions. Then was a second optimization that has been performed at TU Graz by Wolfgang Richter, and they have done actually some CFD calculation, but more specifically, they have been doing some physical model testing in transient condition with a scale ratio 1:25, where they have replicated in time transient the different transient sequence that are the most extreme load cases for the upper and lower surge tank. And this approach allows to address all the free surface flow developing in the surge tank. And finally, when the surge tank design was finalized, and when the turbine supplier, which is Andritz, has performed the model test of the reversible pump turbine, we have updated our model, including all the last data. So the 4-quadrant characteristic, the closing law from Andritz, the last modification of the waterway, including the optimization of the surge tank made by TU Graz. Very important in this power plant is the fact that the design allowed to have very short distance between the reversible pump turbine and the downstream surge tank. There is only 80 meters long between the draft tube and the lower surge tank. And this has been a key in the transient behavior of the unit, because as you know, and as it was well shown today by Professor Chang, the minimum pressure in the draft tube is really a challenge to avoid the so-called water column separation in the draft tube. And therefore, it's requested to have sufficient margin against the vapor pressure. And the fact that there is here a very short distance appear to be a key to avoid low pressure in the draft tube of these pump turbines. Here you have an overview of the Simpson models that has been elaborated. and which includes the headrest tunnel with the gate shaft, with the detailed model of the upper surge tank with its differential effect, the penstock which split in two and then split in four to feed the 4 different pump turbine, the tail race surge tank with differential effect, which has been modeled with detailed modeling, and the tail race tunnel, and then the tail race gate shaft. So during the transient analysis, we have considered normal load cases and exceptional load cases mostly, and we did at the end some verification of catastrophic load cases. The main difference between normal and exceptional load cases is normal load cases are everyday life of the plant, including startup, loading, unloading, but also emergency shutdown, quick shutdown, delayed load rejection, and any combination of two normal load cases like loading plus emergency shutdown in turbine mode or in pumping mode. Exceptional load cases involves the failure of one component, for example, one guide vane failing to close, or one main inlet valve failing to close, or guide vane closing on the security diaphragm, for example. Or a combination of more than two normal load cases if we have like 3 or 4 different sequences in a row. And of course, we had to explore all the different water level conditions when we have maximum head, minimum head, both reservoir maximum water level, Zmax, or both reservoir minimum water level, which we have called Zmin. Here you have the list of the key most critical load cases that we have found for the case of Gouva's pump storage power plant for the design of the surge tank. So you have here the list of 4 normal load cases and 4 exceptional load cases. And each one is targeting one extreme water level, always either maximum or minimum water level of the headrace surge tank, or maximum or minimum water level of the lower tail race surge tank. And we have, again, also 4 load cases, which are exceptional load cases, which I will give more details now. So regarding the exceptional load cases, here are the 2 most critical load cases for headrace tunnel surge tank. So for the critical load case for the maximum water level is the combination of the loading of the 4 units, simultaneous loading of the 4 units. We wait a while until we reach the worst condition for the surge tank and we unload the unit. Then we wait to reload the unit, and after a while we have emergency shutdown. And all this loading and unloading are in phase with the surge tank to maximize the water level in the surge tank. The most critical load case, so here it's an exceptional load cases because we have combination of 4 events together. The most critical load case with respect to the minimum water level of the headrace surge tank was the simultaneous loading of 4 pumps and followed by the emergency shutdown of the 4 units. Actually, this load case is classified as exceptional because it's actually not possible to start the 4 pumps at the same time. We can only start 2 pumps at the same time. So having the 4 pumps loading at the same time is just physically not feasible, but we have still considered it in our transient calculation in case in the future there is an upgrade of the plant that would allow for such simultaneous loading of the 4 pumps at the same time. Regarding the design of the tail race surge tank, the most critical load case with respect to the maximum water level is again the simultaneous loading of 4 pumps followed by emergency shutdown at the worst moment. And the worst case for the minimum water level of the downstream surge tank is simultaneous loading of the 4 units followed by fast unloading with fast reloading, operated on the maximum possible guide vein opening, followed by emergency shutdown. And the load variation are considered to result from primary control and activated through the maximum guide vein opening. So basically, the surge tank has been designed to sustain all these load cases and to offer sufficient safety margin when error margin was also considered. But then during the second optimization phase of the surge tank, some physical model tests have been performed at TU Graz, and the main goal of this physical model test were to assess all the phenomena that we cannot see in the 1D model. So typically all the free surface or air entrainment risk that arise in the flow developing in the surge tank. So the scale ratio between the model and the prototype was 1 to 25. And the goal was to address gravity free surface wave, to address wall shocks of the water when the water is hitting the walls, to address the two-phase flow, to address the risk of air entrainment in the waterway, and a possible air entrapment in the different chambers. What is very interesting in the laboratory of TU Graz is the ability they have to control the discharge over time using a PID controller of valves and pumps, so that they can replicate over time a transient discharge that has been obtained from 1D numerical simulation. So there is a 1D transient discharge target, which is actually replicated over time in the reduced scale model. And here you have basically a comparison between the target and the measured discharge, transient discharge over time. And as you can see, there is a very good match. So basically, it's then possible to impose transient boundary condition during transient test of the surge tank. And here you have an example of the physical model test performed in the laboratory for the most critical load case for the upper surge tank in case of loading plus unloading, reloading, and emergency shutdown, which leads to the maximum water level in the surge tank. And here you can see the nice free jet flowing from the riser of the differential surge tank, which flows down to the main tank of the surge tank. And here you have now a video of the transient behavior of the surge tank in transient conditions, where again the transient boundary discharge is replicated over time, and now you can see of the riser which eventually starts to cool down to the main tank, and you can see that there is no problem with no risk of air entrainment in the waterway, and the proper filling of the riser. Regarding the tail race surge tank, one of the issues that has been found was the fact that when the water was entering in the upper expansion chamber, it was entering with very high velocity, and as a result, the free surface wave, which was propagating in the expansion chamber, finally was hitting the wall at the end of the expansion chamber. And very important is to know that behind this wall, there is actually the gallery, which goes directly back to the transformer hall. So, of course, it's very important that this wall here is not broken by the shock of the water. And as you can see in the original design. Due to the very high jet velocity here, there was a huge heating of this wall. So this is why it was decided to include an inlet ramp, which produced a jump at the inlet of the chamber, and then to install some buffers to dissipate the energy of the free surface wave prior they reach the wall at the end of the surge tank. And this has enables to avoid this huge wall shock at the end of the expansion chamber. Also, special care has been dedicated to prevent from air pocket to develop at the ceiling of the lower expansion chamber. And also, since there is a band between the riser between the two chamber and the lower expansion chamber, there was a significant risk of air entrainment that has been mitigated through some specific local designs. And here you have again a video of the flow coming into the upper expansion chamber of every for the worst case of simultaneous loading of top fan, followed by emergency shutdown at the worst moment. And the video has been actually slowed down with the corresponding scale ratio, so that it's replicating the real time scale of the prototype. And you can see that now, thanks to the ramp at the inlet and also the baffles, the flow developing in the surge tank is quite smooth, and there is no more shock developing in the expansion chamber. And then the chamber is emptying slowly thanks to the ramp and the hole at the bottom of the ramp, which leads to a differential flow of the expansion chamber. So this is all regarding the design phase, and then some years later, after all the plant was built, it was the time of commissioning in 2022. And during the commissioning, we have taken advantage of the digital twin that we have developed at Power Vision Engineering, named HydroClone, which is enabling to replicate in real time the transient behavior of hydropower plant. The idea is to use the detailed 1D Simpson model that was elaborated during the design phase and to run it in real time with measured boundary conditions from the power plant. And then we can replicate in real time the transient behavior, and the simulated quantities can be compared in real time with the measured corresponding quantities. And in case there are significant difference between measurements and simulation, we can raise basically some alarms. So this system includes also graphical user interface and also a database, and it allows also to display in real time the time evolution of the pressure lines all along the waterways and detect possible extreme transient pressure. So having a digital twin of a power plant actually revealed to be extremely useful to detect some possible anomalies which may arise during transient process. So here you have a graph where we have a comparison of the time evolution of the pressure and inlet of Pelton turbines during transient test of emergency shutdown of 3 units. And the comparison between measurements and simulation, the simulation is in blue and the measurements is in red, in orange. And you can see in the measurements, there is suddenly a strong pressure peak of 6 bars, which occurs. And this 6 bar transient overpressure was quite critical in this power plant. But if you don't have the time, the results of the time simulation in blue, it's difficult to know if this transient pressure is normal or not. And then when you have a reference simulation results to compare with, you can quickly detect that something is going wrong. And here, actually, it was demonstrated later on after the test that a main inlet valve of one of the units has closed with completely wrong closing time and has produced this very sharp transient pressure. Fortunately, in this power plant, during the transient test, the water level of the upstream reservoir was at minimum level. So the maximum transient pressure was not problematic, but it would not have been detected unless we would have had we have the corresponding reference simulation results. So that's typical kind of events we want to detect with this hydroclone digital twin. Then, of course, we can detect other possible anomalies like air admission in the waterways, unexpected valve closure like this one, or flow obstruction by external body, or some, for example, some headrest tunnel collapses, or this kind of event. Then the fact of having a digital twin of the plant running in real time give access to some quantities that you can hardly measure. Typically, it gives access to all the pressure all along the headrest tunnel and tailrest tunnel and all pressure along the penstock. So you can detect if locally the transient pressure is exceeding some allowable limit, typically to identify risk of low pressure in the headrest tunnel or extreme transient pressure along the penstock can be detected. And over the long term, you can identify evolution of head losses. You can monitor the unit efficiency and monitor the closing law. And ultimately, since you have access to the time evolution of the pressure all along the waterway over 24 hours per day, 360 days per year, you get access. Also, you can compute the fatigue of the penstock, for example, and estimate the remaining lifetime of the penstock. So this hydroclone system was actually deployed at Gouva's pump storage power plant to follow the commissioning of the power plants. Since, as you have seen, it's quite a challenging waterway, it was of high importance to make sure that the transient behavior of the plant was in line with the simulation done during the design phase. Therefore, we have installed this hydroclone system at site, and the hydroclone was installed on a computer in the power station, and this computer was interfaced with the PLC, with one PLC in the powerhouse, which was collecting all the signals in real time and interfaced with the time domain, the real-time simulation of Simpson on the corresponding computer. And then we were able to compare key hydraulic quantities, typically the pressure at the inlet of the pump turbine, the time evolution of the rotational speed, minimum pressure in the draft tube, and of course, the water level in the surge tanks. Here you have a comparison between simulation and measurements of the time evolution of the water level in the upstream surge tank during some transient event measured during the commissioning. And as you can see, we had already from the very beginning very good agreement between measurements and simulation. Then we found out that the difference between measurements and simulation was related to the fact that the cross-section area of the surge tank was slightly larger than the one that was considered during the design. The diameter was 1% bigger, and we obtained very perfect match with the calibration of this diameter. And actually, since the diameter was bigger, the margin was higher, so it was not an issue at all. But here you can see that we have a perfect match between measurements and simulation, which confirm the proper behavior of the headrest surge tank. Then regarding the tailrest surge tank, again, you have here comparison between measurements and simulation. Here of the pressure in the draft tube, because we don't have directly measurements of water level in the lower expansion chamber. We only had access to water level measurements in the upper expansion chamber. And you have here on the right-hand side a comparison of the time evolution of the water level in the expansion chamber. And when the water reached the expansion chamber, indeed, we had very good agreement between measurements and simulation, and the same applies for the time evolution of the pressure in the draft tubes. Actually, we found out that the friction factor had to be reduced, so we calibrated the friction factor of the tail race tunnel, and it has been reduced as compared to the original target head loss coefficient. And we had also to calibrate the singular head losses of the downstream gate shaft slightly to have a perfect match between simulation and measurements. But again, this comparison between measurements and simulation of the time evolution of pressure and level in the tail race section confirmed the proper hydraulic behavior of the tail race search tank. And then actually we have performed the key transient test of the power plant over 2 days, which is quite a challenge. So during the first day, we have been doing the successive test with 1 unit at full load in turbine mode, 2 units at full load in turbine mode, 3 units and 4 units. So starting in the morning at 220 megawatts and finishing on the evening with the emergency shutdown of 4 units at 800 megawatts. And we did basically the same the following day, but in pumping mode. And this was possible thanks to the fact that it's we have access to real-time comparison between measurements and simulation. So in real time, we can directly compare measurements and simulation and make sure the power plant is behaving as expected. And we were in direct contact with the commissioning team. And after each transient test, we have made verification and provided a very short report to the commissioning team to let them know if everything was in order and if they can proceed with the next transient test with a higher power, which allowed to reduce the number of people we were mobilized for this transient test at site. And I would like to show you some comparison between measurements and simulation performed during the last test in turbine mode with simultaneous emergency shutdown of 4 units at full power, 880 megawatts. Here we have comparison of the time evolution of the transient speed of the unit. We have very good match on the maximum transient overspeed. Then the unit is slowing down. Then we have comparison here of the pressure at the inlet of the spiral case, so we can replicate very well the water hammer time evolution of the pressure. But as it was clearly explained before by Professor Cheng, such kind of low specific speed pump turbine are subject to pressure fluctuations which develop during the transient runaway. And so here we have the superposition between pressure fluctuation and the water hammer phenomena, but all these values were within the allowable range. Then we have here the comparison of the water level in the upper surge tank, the head race surge tank. And in blue, we have the comparison between measurements and simulation of the level in the large tank diameter of 21 meter diameter. And for some reason, that day, the pressure transducer used to measure the water level in the riser was not always functioning properly, especially during the corresponding transient test of emergency shutdown at full power. But fortunately, we had access to the simulated quantity. And since the simulated water level was matching very well with the measured water level in the main tank of 21 meter, we suppose that the time evolution in the riser was also matching well. And actually, it gave access to a view of what was happening in the riser, even though the transducer was not functioning properly. And finally, we have again here some comparison of the water level in the lower surge tank with water level comparison in the upper expansion chamber, which shows a really good match. And interesting is the fact that during the test we have direct access to the piezometric line along the waterway, and we can very quickly extract the pressure envelope. So here is the pressure envelope with the maximum transient pressure all along the waterways, upstream and downstream, maximum pressure and minimum pressure envelope, and we could check that all the pressure were well within the allowable range, admissible range. So just to conclude on this example of application of Simpson, the transient behavior of the Guweiss pump storage power plant was quite challenging because of the very low specific speed and high head of the 4 reversible pump turbines. Also the fact that it had a very long penstock, and it was featuring 2 surge tank upstream and downstream with a differential surge tank design, and also a long tailrace tunnel. And the use of this digital clone ensure continuous diagnosis and direct monitoring in real time during the transient test, which allowed us to perform all the key transient tests from 1 unit to 4 units at simultaneous shutdown in turbine and in pump mode only in 2 days. So now to conclude this presentation, I would like to mention that the Simpson software is quite a unique engineering simulation software, enabling to model hydropower plants, including detailed hydraulic, electrical, and control system in the same platform environment. The Simpson software is actually a powerful tool to address transient behavior in hydropower plants, especially regarding pump storage power plants, which are subject to severe transient phenomena related to the 4-quadrant characteristic of reversible pump turbines. I've not shown it today, but the Simpson software allows also to include 3 surface flow models and 2-phase flow models. It includes also some frequency analysis to perform eigenvalue, eigenvector calculation and force response calculation. And more recently, we have validated the ability to perform co-simulation between 1D and 3D models between Simpson and ANSYS CFX under transient conditions for different test cases for which we have made a validation. And to do this co-simulation between ANSYS CFX and Simpson, we have implemented FMI protocol communication to interface the 2 software and perform co-simulation between 1D and 3D domain. And I've shown also the use of the Simpson software which is a backbone for power plant digital twin hydroclone to monitor transients in hydro power plant. So here are just a couple of pictures of the Guweiss pump storage power plant during the construction phase, and also during the transient test physical model performed in TU Graz. And this is concluding my presentation. So thank you for your attention.
Thank you very much, Christoph, for your very interesting talk. It's fascinating to see how Simpson models together the hydraulic transient with the electric transients. We got 4 questions in the Q&A. The first question is, does Power Vision Engineering offer modeling for projects competing with private companies? And does it also offer training and technical support services for Simpson software buyers?
Yes, actually, yeah. Since we are the official distributor of the Simpson software, indeed, we are distributing the software. We offer training seminar. during which the participant can learn how to use the software and build the first model of their own power plant. Yeah, this is something we do, definitely.
Okay, the next one is Alex Balzarini, who has actually 3 questions related with the slide about validation. Is the headrace tunnel actually much shorter than the penstock, or does the schematic representation simply make it appear this way? This is the first question.
Yeah, maybe I answer it quickly. Yeah, I think so. That was the schematic at the very beginning. Of course, we have seen with Guva's pump storage power plants that headrace might be very long, like 4 kilometers. We have been involved in a project, another pump storage project of Snowy 2.0 in Australia, which is currently under construction, and the headrace tunnel is 17 kilometers long, for example.
Okay, the second question related to validation also, what was the reason for choosing a PRV in this case? Was the implementation of a surge tank challenging due to longitudinal profile of the penstock, or were there other considerations?
Yeah, that's a good question related to this example of Autrive power plant. Actually, there is a surge tank in this power plant, but the PRV has been implemented to prevent the unit to go to excessive transient overspeed. That was the main goal here. The power plant was built more than 100 years ago, and at that time, the turbine and generator supplier was quite afraid of the maximum transient speed of the unit. And to restrict the maximum transient speed of the unit, they were using this PRV. Because, for example, here, the emergency shutdown of the unit 2 at full load results in a transient overspeed only of 10%. And this is possible only because we can close the guide vane in 2 seconds. But of course, if we close the guide vane in 2 seconds without the PRV, the transient pressure would be huge, and we cannot design the penstock for it. And then using the PRV allowed to have fast closing time and limited transient overspeed.
Okay, so indeed, the last question is related, and maybe you already answered. How is the PRV triggered, and how does it operate?
That's a very important question. Because indeed, if the PRV fails to open, basically you burst the penstock. So it has to work. And here it was implemented in a way that the PRV valve is linked very strongly to the guide vane servo motor. So basically there was a oil and mechanical link between the servo motor of the guide vane and the servo motor of the PRV, so that the oil of the servo motor closing is transferred to the servo motor of the PRV, and this oil transfer ensures that you cannot close the guide vane fast without opening the PRV fast. So it was a very robust design that was implemented to make the link between the guide vane servo motor and the PRV servo motor.
Okay, thanks. Yeah, the next participant has let me say, a funny question. Thank you for this very nice presentation. I was wondering, can a civil engineer with weak knowledge on electrical engineering but good judgment for hydraulics become a good Simpson user that carry out hydraulic transient analysis?
Yes, of course, I think so. Here I've shown some electrical applications because the software allows for it, but it's used by hydraulic engineers who are not interested by the electrical part, and they are taking care only of the hydraulic part. And actually, the same apply to the electrical part. There are many users which use only the electrical part without taking care of the hydraulic part. But then the advantage is for the same plant, if you have both models, you can combine it and address some more advanced problems. But you don't need to model the electrical part systematically. You just model it if it is relevant.
Okay. Yeah, maybe a question from my side, because I'm eventually a civil engineer with weak physical intuition regarding electric systems. So if I understood well, in Simpson, you do the coupling at the very high level, at the governing equations level, by means of this analogy, and then you use the same numerical scheme with the same discretization to solve both, no? So when doing the discretization, you need to fulfill a CFL condition. Which of both is more demanding, the electrical side or the hydraulic side?
It's a good question. Actually, the demand on both sides are quite different. On the hydraulic side, it's the number of elements which increase the computation time. Because of course we have to divide the penstock by piecewise by length of 10 meters typically. So with 1,000 kilometers penstock, you need 100 elements, which end up with 201 differential equation to solve. And on the electrical side, you have less equation because you don't need this spatial discretization. You have a bit less equation, but then you need a very short integration time steps because the electrical time constant are way shorter than the hydraulic time constant. So the complexity or the computational time increase for different reasons on both sides. But then, of course, when you combine both, you have both. You combine both complexity and the computational time is increasing, but still we remain to have a reasonable computational time even for hydroelectric system, and we can achieve for most of the cases still real-time simulation for hydroelectric models.
So the time step between the electric side and the hydraulics, is it the same or are they different?
Yeah, it's the same. It's the same.
It's
But
the same.
of course, when we solve purely hydraulic system, we can afford a higher integration time step. But when we include the electrical part, we have to reduce the integration step, which is the same for all the elements. And then we combine a high number of equations from the hydraulic side with short integration time step from to resolve the electrical side. But actually, the final computing time remains reasonable, I would say.
Okay. I see, Elena, that you have your hand raised. Any comments?
Okay. Christophe, thank you very much for your presentation with very interesting case studies. I'm curious in one thing. For example, in terms of the numerical models that you use Simulink or from MATLAB or other type of language?
Okay. Actually, originally we have prototyped with MATLAB, but then everything is implemented in Simpson with, let's say, Pascal programming language, which nowadays is Delphi programming languages.
Okay. Another question is about how do you differentiate the shape of the Francis turbines runner associated with specific speed, of course.
Yes,
because
exactly.
Francis can cover a big range of specific speed. I don't know how do you cover this type of range.
Yeah. You're right. So depending on the specific speed, of course, the shape of the runner is different, and then the hydraulic characteristic of the machine is different. Originally, the user had to provide the turbine characteristic, but nowadays we have a library of turbine characteristic for Francis turbine. We have another one for reversible pump turbine, which
Sutter parameters, no? Sutter parameters.
Yeah,
Sutter.
of course, we use the Sutter transformation on the background to perform the interpolation on the characteristic, but we have a library with 40 different Francis turbine characteristics covering the full range of typical specific speed from NQ25 to NQ70, more or less, and we have also a similar library of Pantherman characteristics available, but
Yes.
as additional libraries.
And in line with the question from David, did you notice any resonance effects when we make the connection between hydraulic and electric components?
You mean resonance physical one? You mean?
Numerical.
Numerical? No, it worked fine. No,
Okay.
no issue. Of course, it's finite difference method models on the hydraulic side, so reducing the integration time step due to the electrical system makes it more accurate on the hydraulic side, so we had absolutely no problem.
Okay, perfect. Thank you.
You're welcome.
So we have two more questions in the Q&A. The next participant wonders if you can describe cavitation with Simpson.
Yeah, good question. We have actually models of cavitation, different models. We have implemented models of water column separation based on discrete gas cavity models that was described in literature, and we have validated against available measurements and simulation from method of characteristic provided by Anton Bergant. I guess most of you know him. And we can also model cavitation that develop, for example, in draft tubes of Francis turbine, typically vortex rope developing at part load or at full load. So we have specific models for the cavitation developing in draft tubes to perform stability and, or let's say, resonance risk analysis for operation at part load. And then we can include pressure fluctuation source and check for risk of resonance of the waterway at part load. And we could check also the risk of self-excitation at full load operation. So that's completely different model as compared to the water column separation model, since the way the cavitation is arising is quite different. Yeah, so that's quite different models, but they are implemented in Simpson and have been validated for different cases.
Okay, thank you. And the last question, besides water column acceleration time and runaway speed, what other parameters, if any, govern the closure and opening time of the turbine? Is this charge an important parameter in determining the closure and opening time of the turbine? What is the maximum closure and opening time of Francis turbine? What you have experienced,
Yeah, that's really the goal of such a kind of 1D transient calculation, is to optimize the closing law of the guide vanes of turbines to have the best compromise between maximum transient pressure in spiral case, minimum pressure in the draft tube, and the transient overspeed of the unit. Now the typical range of closing time depends very much on the waterway itself. There are units you can see here, the one equipped, since it is equipped with PRV, the guide vanes are closing in 2 seconds or 2.5 seconds. And in some power plants, to mitigate the water hammer, we had to close the guide vanes in more than 100 seconds to avoid excessive pressure in the spiral case, for instance. So I would say the most extreme closing time were ranging between 2 seconds and around 100 seconds, I would say, for Francis turbine.
Okay, great. Thank you very much. I see no more questions coming up. So again, Christoph, thank you very much for your very interesting presentation and nice discussion. Before closing the session, I would like to remind the participants that tomorrow we'll start a bit later at 1 p.m. Central European Time. So please do the conversion in your respective time zone. And we'll have also 3 speakers. So the first speaker will be from Hohei University, also on CFD, like this morning. Then a talk about Alievi software from UPV, University Polytechnic of Valencia, with Enrique Cabrera. And then a talk by Trey Walters on AFT Impulse software. So looking forward for that. And yeah, I hope to see you all tomorrow. Thank you and have a nice day, afternoon and evening. Bye-bye. See you.